My name is David Ondrej, and in this video, I'll be completing one of Andrej Karpathy's famous lectures on neural networks. My goal with this video is for us to learn AI concepts that would normally take years of college education in just a few hours. And that is only possible because Andrej Karpathy is one of the greatest teachers in the history of AI. This comment says it all. The fact that this video is free to watch feels illegal. With that said, enjoy.
Hello, my name is Andrej, and I've been training deep neural networks for a bit more than a decade. And in this lecture, I'd like to show you what neural network training looks like under the hood. So in particular, we are going to start with a blank Jupyter notebook, and by the end of this lecture, we will define and train a neural net. And you'll get to see everything that goes on under the hood and exactly sort of how that works on an intuitive level.
Okay, so let me at least replicate this. I've created an empty Google Colab, which will serve as the Jupyter notebook. So yeah, let's go.
Now, specifically what I would like to do is I would like to take you through building of Micrograd. Now, Micrograd is this library that I released on GitHub about 2 years ago, but at the time I only uploaded the source code, and you'd have to go in by yourself and really figure out how it works. So in this lecture, I will take you through it step by step and kind of comment on all the pieces of it. So what is Micrograd and why is it interesting? Micrograd is basically an Autograd engine. Autograd is short for automatic gradient. And really what it does is it...
Okay, so I think I need to understand the concept of gradients a little better. So let's use Perplexity for that. In AI, a gradient is basically a measure of how much a small change in one thing affects another thing. The key things to remember about gradients in AI: they point in the direction of the steepest increase. They help guide the learning process. They're used in many optimization algorithms, especially for training neural networks. Okay.
It implements backpropagation. Now, backpropagation is this algorithm that allows you to efficiently evaluate the gradient of some kind of a loss function with respect to the weights of a neural network. And what that allows us to do then is we can iteratively tune the weights of that neural network to minimize the loss function and therefore improve the accuracy of the network. So backpropagation would be at the mathematical core of any modern deep neural network library, like say PyTorch or JAX. So the functionality
Shout out Jeffrey Hinton
of Micrograd is, I think, best illustrated by an example. So if we just scroll down here, you'll see that Micrograd basically allows you to build out mathematical expressions. And here what we are doing is we have an expression that we're building out where you have two inputs, A and B. And you'll see that A and B are -4 and 2, but we are wrapping those values into this value object that we are going to build out as part of Micrograd. So this value object will wrap the numbers themselves. And then we are going to build out a mathematical expression here where A and B are transformed into C, D, and eventually E, F, and G. And I'm showing some of the functionality of Micrograd and the operations that it supports. So you can add two value objects, you can multiply them.
Okay, so far, so good. I'm hanging on. Maybe I shouldn't jinx it.
Constant power. You can offset by 1, negate, squash at 0, square, divide by constant, divide by it, etc. And so we're building out an expression graph with these two inputs A and B, and we're creating an output value of G. And Micrograd will, in the background, build out this entire mathematical expression. So it will, for example, know that C is also a value. C was a result of an addition operation, and the...
Oh, so it's not like, C is just assigned a number. It knows like the history of basically how C was formed. At least that's how I understand it.
Nodes of C are A and B because and it will maintain pointers to A and B value objects. So we'll basically know exactly how all of this is laid out. And then not only can we do what we call the forward pass, where we actually look at the value of G, of course, that's pretty straightforward. We will access that using the .data attribute. And so the output of the forward pass, the value of G, is 24.7, it turns out. But the big deal is that we can also take this G value object and we can call .backward.
So I assume this is going to be like the function that does the backpropagation. We'll see.
And this will basically initialize backpropagation at the node G. And what backpropagation is going to do is it's going to start at G and it's going to go backwards through that expression graph and it's going to recursively apply the chain rule from calculus. And what that allows us to do then...
Yeah, seems like I'll have to, brush off my math concepts, but that's good. Like I used to be good at math, then some high school teachers made me not that interested in it, but yeah, we'll have to brush off some Fs, I think. Like,
we're going to evaluate basically the derivative of G with respect to all the internal nodes like E, D, and C, but also with respect to the inputs A and B. And then we can actually query this derivative of G with respect to A. For example, that's A dot grad. In this case, it happens to be 138. And the derivative of G with respect to B, which also happens to be here, 645. And this derivative, we'll see soon, is very important information because it's telling us how A and B are affecting G through this mathematical expression. So in particular, A dot grad is 138. So if we slightly nudge A and make it slightly larger, 138 is telling us that G will grow, and the slope of that growth is going to be 138.
okay, so we see that in this case, B has a higher effect on the result of G than A.
Growth of B is going to be 645. So that's going to tell us about how G will respond if A and B get tweaked a tiny amount in a positive direction. Okay. Now, you might be confused about what this expression is that we built out here. And this expression, by the way, is completely meaningless. I just made it up. I'm just flexing about the kinds of operations that are supported by Micrograd. What we actually really care about are neural networks. But it turns out that neural networks are just mathematical expressions, just like this one, but actually slightly a bit less crazy even. Neural networks are just a mathematical expression. They take the input data as an input, and they take the weights of a neural network as an input, and it's a mathematical expression, and the output are your predictions of your neural net or the loss function. We'll see this in a bit. But basically, neural networks just happen to be a certain class of mathematical expressions. But backpropagation is actually significantly more general. It doesn't actually care about neural networks at all. It only cares about arbitrary mathematical expressions. And then we happen to use that machinery for training of neural networks. Now, one more note I would like to make at this stage is that, as you see here, Micrograd is a scalar-valued Autograd engine.
Okay, so first off, I would like to try to understand backpropagation better. Here's a simple explanation. So backpropagation is basically like reflecting on your actions. So you do something, and then you reflect how it went, and you would use, the final state, what you've learned, to optimize for the best possible actions in the future. Now, the most common question I get all the time is, David, I've learned how to build AI agents, I've learned how to use ChatGPT, but how do I make money with AI? And even as you can see, when I ran this poll on my channel, by far the most people are interested in how to make money with AI, which prompted me to start working on this exclusive workshop, which I'll be releasing in the next few days. And the reason I'm announcing it now is when it releases, the price for the community will nearly double. So if you want direct access to myself in the form of weekly calls, if you want to be in a network of over 500 people at the cutting edge of AI, then make sure to join. It's going to be the first link in the description. See you inside.
The level of individual scalars like -4 and 2. And we're taking neural nets and we're breaking them down all the way to these atoms of individual scalars and all the little pluses and times. And it's just excessive. And so obviously you would never be doing any of this in production. It's really just done for pedagogical reasons because it allows us to not have to deal with these n-dimensional tensors that you would use in a modern deep neural network library. So this is really done so that you understand and refactor out backpropagation and chain rule and understanding of neural network training.
The reason he built this, at least that's what I think, is to show how deep neural networks actually work. Because, normally you're using these libraries and it's like multiple levels of abstraction above the actual math. But this brings us closer to understanding the fundamentals. Now, one more thing I want to do is really understand the differences between vectors, scalars, and tensors. Complexity. Scalars are the simplest, vectors are direction, tensors can have many dimensions. Information. Tensors can store more complex data than vectors, which store more than scalars. Uses. Scalars for basic quantities, vectors for directional data, tensors for advanced AI ML tasks.
Actually want to train bigger networks, you have to be using these tensors, but none of the math changes. This is done purely for efficiency. We are basically taking all the scalar values, we're packaging them up into tensors, which are just arrays of these scalars. And then because we have these large arrays, we're making operations on those large arrays that allows us to take advantage of the parallelism in a computer. And all those operations can be done in parallel, and then the whole thing runs faster. But really none of the math changes, and that's done purely for efficiency. So I don't think that it's pedagogically useful to be dealing with tensors from scratch. And that's why I fundamentally wrote Micrograd, because you can understand how things work at the fundamental level, and then you can speed it up later.
Oh, so like instead of using tensors, which, are definitely way more complex than scalars, what Andrej Karpathy did is basically did the same as you would be using in like more advanced AI frameworks, like maybe PyTorch or TensorFlow, but he replicated it with scalars.
Okay, so here's the fun part. My claim is that Micrograd is what you need to train neural networks, and everything else is just efficiency. So you'd think that Micrograd would be a very complex piece of code, and that turns out to not be the case. So if we just go to Micrograd, and you'll see that there's only 2 files here in Micrograd. This is the actual engine. It doesn't know anything about neural nets, and this is the entire neural nets library on top of Micrograd. So engine and nn.py. So the actual backpropagation Autograd engine that gives you the power of neural networks is literally...
Wow, 94 lines of code. Check this out.
Autograd engine.
That's crazy. That's honestly a flex, like.
Gives you the power of neural networks is literally 100 lines of code of like very simple Python, which we'll understand by the end of this lecture. And then nn.py, this neural network library built on top of the Autograd engine, is like a joke. It's like we have to define what is a neuron, and then we have to define what is a layer of neurons, and then we define what is a multi-layer perceptron, which is just a sequence of layers of neurons.
I have a feeling that, when Karpathy says like, oh, this is just simple Python, it's not going to be a simple Python, but hey, let's see.
And so it's just a total joke. So basically, there's a lot of power that comes from only 150 lines of code. And that's all you need to understand neural network training, and everything else is just efficiency.
This is a good promise. Like by the end of this, hopefully we'll understand neural network training. One of the fastest, most efficient ways to learn this. Because like in college, it would take you 4 years.
To efficiency, but fundamentally that's all that's happening. Okay, so now let's dive right in and implement Micrograd step by step. The first thing I'd like to do is I'd like to make sure that you have a very good understanding intuitively of what a derivative is and exactly what information it gives you. So let's start with some basic imports that I copy-paste in every Jupyter notebook always.
Okay, so maybe we just try to understand that. A derivative in mathematics is a fundamental concept that represents the rate of change of a function. Okay, so I guess these are good illustrations. In AI and machine learning, derivatives are crucial for optimizing models through a process called gradient descent.
And let's define a function, a scalar valued function, f of x, as follows. So
Okay. We define a function... Wait, slow down.
A scalar valued function, f of x, as follows.
F of x.
So
return 3 times x to the power of 2 minus 4 times x. Okay, so a random arbitrary function. 3 times x to the power of 2 plus or minus 4 times x plus 5. Minus 4 times x plus 5.
I just made this up randomly. I just wanted a scalar valued function that takes a single scalar x and returns a single scalar y.
Yeah, simple
and we can
enough.
call this function, of course, so we can pass in, say, 3.0 and get...
Yeah, let's test it out as well. What's the shortcut? Control M. Whatever. So let's do f of 5. 60. Yeah.
Get 20 back. Now, we can also plot this function to get a sense of its shape. You can tell from the mathematical expression that this is probably a parabola. It's a quadratic. And so if we just create a set of scalar values that we can feed in using, for example, a range from -5 to 5 in steps of 0.25.
This is what I mean. Like Andrej Karpathy says, like this is just simple Python, like no big deal, and then he's just suddenly going ham. Okay, let me
create a set of scalar values that we can feed in using, for example, a range from -5 to 5 in steps of 0.25.
Sure. One more time.
Create a set of a parabola. It's a quadratic. And so if we just create a set of scalar values that we can feed in using, for example, a range from -5 to 5 in steps of 0.25.
Is an array going from -5 to 5 excluded. Okay, so yeah, including the lowest value but excluding the highest value, and by jumps of 0.25. So yeah, numpy arrange -5, 5 by 0.25, and then we do one more just to call it. Yeah, same output.
So axis is just from -5 to 5, not including 5, in steps of 0.25. And we can actually call this function on this numpy array as well. So we get a set of y's if we call f on axis. And
okay, yeah, so now we're just applying the function to a y. We need a y using this function. So these values, might seem more random, but it's simply xs went through this function we declared earlier. Looks right.
These y's are basically also applying the function on every one of these elements independently. And we can plot this using matplotlib. So plt.plot x's and y's, and we get...
Oh my god. So beautiful, man. I really need to step up my Python library skill set.
A nice parabola. So previously here we fed in 3.0 somewhere here, and we received 20 back, which is here, the y-coordinate. So now I'd like to think through what is the derivative of this function at any single input point x, right? So what is the derivative at different points x?
Okay, so what is the rate of change or slope at any given point? So that's what he means when he says, like, what is the derivative? Just the rate of change, slope at any given point
of this function. Now, if you remember back to your calculus class, you've probably derived derivatives. So we take this mathematical expression, 3x squared minus 4x plus 5, and you would write it out on a piece of paper, and you would, apply the product rule and all the other rules and derive the mathematical expression of the great derivative of the original function. And then you could plug in different x's and see what the derivative is. We're not going to actually do that because no one in neural networks actually writes out the expression for the neural net. It would be a massive expression. It would be, thousands, tens of thousands of terms. No one actually derives the derivative, of course. And so we're not going to take this kind of like symbolic approach. Instead, what I'd like to do is I'd like to look at the definition of derivative and just make sure that we really understand what the derivative is measuring, what it's telling you about the function. And so if we just look up derivative.
Okay, now I don't feel so bad about looking terms up because Karpathy does it. I mean, obviously he knows what it is, but like, just the fact that he looks it up for clarity is nice.
We see that, okay, so this is not a very good definition of derivative. This is a definition of what it means to be differentiable. But if you remember from your calculus, it is the limit as h goes to 0 of f of x plus h minus f of x over h. So basically what it's saying is if you slightly bump up, you're at some point x that you're interested in, or a, and if you slightly bump up, you slightly increase it by small number h, how does the function respond? With what sensitivity does it respond? What is the slope at that point? Does the function go up or does it go down, and by how much? And that's the slope of that function, the slope of that response at that point. And so we can basically evaluate the derivative here numerically by taking a very small h. Of course, the definition would ask us to take h to 0. We're just going to pick a very small h, 0.001. And let's say we're interested in point 3.0. So we can look at f of x, of course, as 20.
Okay, let me use the same numbers. So control MB, h equals 0, 0, 1, x equals how much? 3, and then f of x, call the function. Oops, didn't mean to.
And now f of x plus h. So if we slightly nudge x in a positive direction, how is the function going to respond? And just looking at this, do you expect f of x plus h to be slightly greater than 20? Or do you expect it to be slightly lower than 20? And since it's 3...
Yeah, we can see it on the graph pretty clearly.
is here, and this is 20. If we slightly go positively, the function will respond positively. So you'd expect this to be slightly greater than 20. And now by how much is telling you the the strength of that slope, right? The size of that slope. So f of x plus h minus f of x, this is how much the function responds.
Oh, so I mean, that's not that difficult. You know, when you pull up the Wikipedia, you look at the mathematical expressions, it's like, it can be super intimidating, but actually writing it out in code, doing it yourself, and especially with Andrej Karpathy's excellent explanation, it gives a lot of clarity.
Responded in a positive direction, and we have to normalize by the run, so we have the rise over run to get the slope. So this, of course, is just a numerical approximation of the slope.
Okay, so now that was a bit more complex. Need to replay that part, to be honest. We just, oh, okay.
The strength of that slope, right? The size of that slope. So f of x plus h minus f of x, this is how much the function responded in a positive direction. And we have to normalize by the run, so we have the rise over run to get the slope. So this, of course, is just a numerical approximation of the slope, because
rise over run. I'm pretty sure I know these terms in Czech, but I haven't learned any math in English. So another way of referring to slope, ratio of rise. Oh.
Make h very, very small to converge to the exact amount. Now, if I'm doing too many zeros, at some point, I'm going to get an incorrect answer, because we're using floating point arithmetic, and the representations of all these numbers in computer memory is finite, and that's...
Okay, so this is actually a fascinating quirk of float numbers. You know, as he said, I mean, he explains it better than me, but like, you know, if you didn't understand that float isn't a perfect representation, because we're still using like bits and bytes like in a computer, then you would be confused by this, but the way he explains it is really good.
At some point, I'm going to get an incorrect answer, because we're using floating point arithmetic, and the representations of all these numbers in computer memory is finite, and at some point we get into trouble. So we can converge towards the right answer with this approach. But basically, at 3, the slope is 14. And you can see that by taking 3x squared minus 4x plus 5 and differentiating it in our head. So 3x squared would be 6.
So we're basically taking one point of the function, in this case 3, and trying to see the slope of the curve at that point, right? So obviously it's different towards 0 here, different at -1, -5, different at 3. So we're trying only for that specific point, because you cannot really do it for the function as a whole, because, you know, it changes. But then at a single point you can. So you just like know how steep it is at that point.
X minus 4, and then we plug in x equals 3, so that's 18 minus 4 is 14. So this is correct. So that's at 3. Now how about the slope at, say, -3? What would you expect for the slope? Now, telling the exact value is really hard, but what is the sign of that slope?
Yeah,
so
it's going to be decreasing.
-3, if we slightly go in the positive direction at x.
I mean, yeah, in a positive direction, the y value gets lower, but in a negative direction, y value gets higher.
The function would actually go down, and so that tells you that the slope would be negative. So we'll get a slight number below 20. And so if we take the slope, we expect something negative 22. Okay.
You know, it's really a shame that in school, math doesn't start with AI. Like, imagine you had like 3 months of AI sparking everybody's interest, like artificially intelligent machines, like making computers think, making computers intelligent. That would interest way more people. And then after 3 or 4 months, you would see like, you know, some math is actually useful in AI to understand how this works, to build these intelligent neural networks. I guarantee you way more people would actually pay attention and learn math. Because right now, if you're watching this without any math experience or coding experience, you're probably like researching every 5 seconds what he's saying. So yeah, it's unfortunate. AI should be the way. AI should be the intro into math, not just like giving students math like, oh, trust me, this is useful, and 99% of them will never use it and forget it in 5 days.
And at some point here, of course, the slope would be 0. Now for this specific function, I looked it up previously, and it's at point 2 over 3. So at roughly 2 over 3.
Okay, wait, let me do this. I want to do the testing, even though it's kind of basic. So we have, yeah, negative slope. Wait, it's not the same as his, though.
At some point here.
Is that because of the... Oh, yeah. Because he has a few more zeros. And at 2 over 3, it should be 0, but yeah, it is. So like 0.66. Slope is 0, meaning... Yeah, meaning on the y-axis, changes on the y-axis. So here, basically, arrow would be pointing to the right completely, 90-degree angle. So the slope, I mean, again, I'm relearning basic math language, basic math lingo in English because I learned all of my math in Czech. So it's basically changes on the y-axis. Yeah, that's the slope, I guess.
Of course, the slope would be 0. Now for this specific function, I looked it up previously, and it's at point 2 over 3. So at roughly 2 over 3, that's somewhere here, this derivative would be 0. So basically, at that precise point, at that precise point, if we nudge in a positive direction, the function doesn't respond. This stays the same almost. And so that's why the slope is 0. Okay, now let's look at a bit more complex case. So we're going to start...
But if you're confused about this number, it's basically like a super low number, close to 0.
If we nudge in a positive direction, the function doesn't respond. This stays the same almost. And so that's why the slope is 0. Okay, now let's look at a bit more complex case.
Okay. As if everything we've been doing was super easy. I mean, I guess. Wasn't too bad. Okay.
So we're going to start, complexifying a bit.
Yeah,
so now
let's define these. A, B, C, D, print D. Getting more complex. A, B, C, then D. Then we're printing D. Now 2 minus 3 and 10. And then whatever. 2 minus 3 and 10. I wonder why he's doing them in floats. Whether that's like a just good habit. Or I don't know, maybe I can ask, like, I'm gonna take a screenshot of Karpathy, put it into Perplexity, and then screenshot of this code. I'm watching a tutorial by Karpathy, and he keeps putting all values into float numeric depictions. For example, instead of saying x equals 2, he always does x equals 2.0. Is there any reason for this? Answer in short. In programming tutorials, especially those related to machine learning and AI, using float values like 2.0 instead of 2 is common for consistency and to avoid potential issues with data types. This practice ensures all numbers are treated as floating point, which is crucial for many mathematical operations and algorithms in these fields. It also helps prevent unexpected type conversions. Okay, so yeah, just basically like a good habit. So let's learn that habit and do it as well. What is D? A times B plus C. Okay, A times B plus C. Let's run it. And D is 4. So A times B minus 6 plus C 10. Yeah.
now we have a function here.
But if I were to make a guess, that wasn't the complex part he meant.
With output variable D, that is a function of 3 scalar inputs, A, B, and C. So A, B, and C are some specific values, 3 inputs into our expression graph, and a single output D. And so if we just print D, we get 4. And now what I'd like to do is I'd like to again look at the derivatives of D with respect to A, B, and C. And think through, again, just the intuition of what this derivative is telling us. So in order to evaluate this derivative, we're going to get a bit hacky here. we're going to again have a very small value of h, and then we're going to fix the inputs at some values that we're interested in. So this is the point ABC at which we're going to be evaluating the derivative of d.
Okay, before we go further, let me just replicate this as well. Control M B. So we define a small h. This is 1/10,000th in this case. Yes. 3 zeros, and then copy these over. Inputs. And we still copy the d over. Okay.
With respect to all a, b, and c. Evaluate this derivative. We're going to get a bit hacky here. We're going to again have a very small value of h, and then we're going to fix the inputs at some values that we're interested in. So this is the point ABC at which we're going to be evaluating the derivative of d with respect to all a, b, and c at that point. So there's the inputs, and now we have d1 is that expression. And then we're going to, for example, look at the derivative of d with respect to a. So we'll take a and we'll bump it by h.
Okay. d1.
And then we'll get d2 to be the exact same function. And now we're going to print
a plus equals h. But why is d2 the same function? Why aren't we using... I mean, yeah, a has changed. What am I saying?
You know, f1, d1 is d1, d2 is d2, and print slope. So the derivative, or slope...
Yeah, so now we're getting a bit more advanced. d1, 1, 2, d2, and now we're going to use the derivative to get the slope. So if I were to guess this, except using our functions, not the function f.
Here will be, of course, d2 minus d1 divide h. So d2 minus d1 is how much the function increased when we bumped the specific input that we're interested in by a tiny amount. And this is then normalized by h.
d2 minus d1 divided by h. Interesting.
To get the slope. So, yeah.
Are we going to visualize
so this? So if I just run this, we're going to print d1, which we know is 4. Now d2 will be bumped, a will be bumped by h. So let's just think through a little bit what d2 will be printed out here. In particular, d1.
Okay, so a is increased by a small amount. We're reducing, since it's, being multiplied by a negative number, we're gonna have a lower result. A little bit lower.
1 will be 4. Will d2 be a number slightly greater than 4 or slightly lower than 4? And that's going to tell us the sign of the derivative. So we're bumping a by h. B is minus 3, C is 10. So you can just intuitively think through this derivative and what it's doing. A will be slightly more positive, but B is a negative number. So if A is slightly more positive, because B is negative 3...
This is crazy. Like, why is he going so slow on basic math and then, just like sprinting through the advanced AI concepts? I don't know, maybe it's just me, but like, I wish like he went this granular on explaining some of the more advanced stuff, but then like explaining basic algebra, like why is he going so fascinating, man.
We're actually going to be adding less to d. So you'd actually expect that the value of the function will go down. So let's just see this. Yeah, and so we went from 4 to 3.9996. And that tells you that the slope will be negative, and then will be a negative number because we went down, and then the exact number of slope will be, exact amount of slope is -3. And you can also convince yourself that -3 is the right answer mathematically and analytically, because if you have a times b plus c and you are, you have calculus, then differentiating a times b plus c with respect to a gives you just b. And indeed, the value of b is -3, which is the derivative that we have. So you can tell that that's correct. So now if we do this with b, so if we bump b by a little bit in a positive direction, we'd get different.
B plus e equals h. So since b is a negative number, we would actually go in a positive direction here. Let me comment this out. Yes.
Slope. So what is the influence of b on the output d? So if we bump b by a tiny amount in a positive direction, then because a is positive,
I want to understand something he said a bit earlier.
You have calculus, then differentiating a times b plus c with respect to a gives you just b.
A times b plus c respect to a. Okay. Let me just use perplexity here. Actually, I'm gonna, instead of a screenshot, such a small resolution, let me just paste it in. Help me find the value. Okay, wait. What does it say?
Because if you have a times b plus c, exact amount of slope is -3. And you can also convince yourself that -3 is the right answer mathematically and analytically, because if you have a times b plus c and you are, you have calculus, then differentiating a times b plus c with respect to a gives you just b.
Okay. Help me understand how differentiating a times b plus c with respect to a gives us b. I should probably also include these. Separate this.
B. And indeed, the value of b is -3.
Let's go pro here. Might be another case of English translation to check. Probably not though. The derivative of a times b plus c with respect to a is indeed b. Here's a concise explanation. Product rule. When differentiating a times b, we treat b as a constant since we're differentiating with... Man. Okay. Constant rule. Derivative of a constant, c in this case, is always 0. Sum rule. We differentiate each term separately and add the results. So, dda I mean, this was too simplistic, but I still wanted to use simple. You're right, let's break it down more clearly. Think of a times b plus c as a line on a graph. A is like a slider we can move. When we move a, the line changes. The derivative tells us how fast the line changes when we move a. B is exactly how much the line goes up or down when we increase A by 1. C doesn't change when we move A. Okay, better explanation, but you still left out Y. Y, and then just copy this part. Y is, and then Y, it doesn't change when we move A. YB is a change. In A times B, B acts as a multiplier for A. Okay, when A is increased by 1, the product increases by B. Yes. I mean, even a simple word like product is confusing to me. I mean, this is gonna be, yeah, this is the what I'm looking for. So yeah, I mean, this is the Czech translation, but still, like, I'm getting confused by the most simplest of math terms purely because I've learned it in a different language, which is annoying, but hey, at least I'm gonna learn English maths. Example, if A is 2 and B is 3, AB is 6, yes. If A becomes 3, AB is 9, yes. The change is 3, which is B. Why C doesn't change? C is a constant term, not connected to A. Oh my god, yes. Because of this equation, of our equation, C is just added on top. So it doesn't influence A. So only B influences A, so... Man!
3, which is the derivative that we have. So you can tell that that's correct. So now if we do this with B, so if we bump B by a little bit in a positive direction,
2, no?
we'd get different slopes.
The slope would be 2, surely. B. Let's play this out. Yes. Okay, I've gained understanding of English math.
So what is the influence of B on the output D? So if we bump B by a tiny amount in a positive direction, then because A is positive, we'll be adding more to D, right? So, and now what is the sensitivity? What is the slope of that addition? And it might not surprise you that this should be 2. And why is it 2? Because D of D by dB, differentiating with respect to B, would give us A. And the value of A is 2. So that's also working well. And then if C gets bumped a tiny amount in H by H, then of course A times B is unaffected. And now C becomes slightly bit higher. What does that do to the function? It makes it slightly bit higher because we're simply adding C. And it makes it slightly bit higher by the exact same amount that we added to C. And so that tells you that the slope is 1.
Oh, 1. Okay.
That will be the...
I guess I'm still a noob.
The rate at which D will increase as we scale C. Okay, so we now have some intuitive sense of what this derivative is telling you about the function. And we'd like to move to neural networks.
Oh yeah, it's basically, the way to visualize it is like C times 1. You know, if you were to have another multiplier in this equation.
Now, as I mentioned, neural networks will be pretty massive expressions, mathematical expressions. So we need some data structures that maintain these expressions. And that's what we're going to start to build out now. So we're going to build out this value object.
C plus equals H going in a positive direction by the exact same amount. And this is basically 1.
Object that I showed you in the README page of Micrograd. So let me copy paste a skeleton of the first very simple value object.
Okay, let me actually write down all the code, because this is a tip, even with AI tools like coding assistants, writing the code manually is by far the best way to gain the understanding, right? Especially if you're trying to learn. If you're doing something you've already done 1,000 times and you don't need to learn how to, call OpenAI API or something, then yeah, feel free to just copy paste or whatever. But if you're like trying to learn, which is what I'm trying to do now, typing every single line of code manually is huge. It's just a huge difference. So let's do that. class value, we declare a new class, 2 functions. Oh my god, man. My Google Colab. Oh no, shift enter, just enter. Feels so unnatural, but whatever. Def initializer function self and data. Probably know this, to be honest. Self.data equals data. Now we do rep. This one is not as common though. Return f value. Interesting. So this is an f string. Oh. This looks way complicated than it actually is, but this is just text and then but this will be formatted incorrectly, I guess. There is not the second. Maybe that's a mistake. Maybe, you know, the second parenthesis is missing. Obviously a small detail, but whatever.
So class value takes a single scalar value that it wraps and keeps track of, and that's it. So we can, for example, do value of 2.0, and then we can...
You know what, let me actually go complete the noob and just, you know, take a screenshot. Explain this piece of code in simple terms. Why is it uploading so long? This code defines a simple Python class called value. Here's a breakdown. The class has a constructor method that initializes an object with a data attribute. There's a wrapper method that provides a string representation of the object. When you create a value object, you can give it some data. The object stores this data internally. If you try to print the object and convert it into a string, it will show value data equals x. But then that's missing. Yeah, there should be the curly brace. Whatever, I'm gonna add it. Actually, I'm not gonna add it, but we're gonna keep it in mind. Potentially missing. Again, it's only like syntax stuff. Won't change anything about the program.
We can look at its content and
wait a second, what happened?
And that's it. So we can, for example, do value of 2.0, and then we can get we can look at its content, and Python will internally use the rep.
Such a good habit making it into float.
Function to return this string. Whoops. Like that. So this is...
I've noticed a syntax error. Not that it makes me any good or any better of a programmer, but hey.
This is a value object with data equals 2 that we're creating here. Now what we'd like to do is we'd like to be able to have not just like 2 values, but we'd like to do a plus b, right? We'd like to add them.
Okay, so b value minus 3, and now we get an error. And 0 a plus b, but it's objects, so unsupported operand type for value type error.
So currently you would get an error because Python doesn't know how to add two value objects.
Yeah.
So we have to tell it. So here's addition. So you have to.
Okay, but how does it know? Okay, this is going to be another dumb question, but like... Okay, but how does Python know to use the second function when someone wants to print out the object? Python uses the repr method automatically when you try to print out object. Okay, so these are built-in methods. It's part of Python's dunder, double underscore method system. Okay, teach me the most fundamental methods in Python's dunder. I should probably know this. Python's dunder double underscore methods. Dunder are special methods that allow you to define how objects of a class behave in various situations. Here are some of the most fundamental. Why don't I know this? I mean, obviously I've seen this one, but man, maybe I suck. Okay, the constructor method. Double underscore init, double underscore. Called when creating a new instance of a class, it initializes the object's attributes. Repr method, representation, returns a string representation of the object, typically used for debugging and development. str, returns a string representation for end users. If not defined, repr is used as a fallback. Okay. Len, defined when a length is called on an object. Get item allows you to use square brackets notation for indexing or key access. Set item, key value. Defines behavior for assigning values using. Okay, which are we using right now? Add. We're using add. That's, I guess, the default. Yeah, but basically these are built-in Python methods that... Okay, so I'm going to ask. So basically these are built-in Python methods that make working with objects and classes easier, right? Exactly, these are built-in Python methods, specifically dunder methods, that make working with object and classes easier and more intuitive. Okay, so let's do this one. Add dunder method. See, this is the main value of this video, just seeing me be a total noob and like learn the basics that I should know otherwise. Output equals value, so self.data plus other.data. Alright, so now this should work. Beautiful, man, so beautiful. Just by defining a new method.
To basically use these special double underscore methods in Python to define.
And now he explains it. Oh my god, maybe I should be a bit more patient.
Define these operators for these objects. So if we call if we use this plus operator, Python will internally call a.add of b. That's what will happen internally. And so b will be the other, and self will be a. And so we see that what we're going to return is a new value object, and it's just it's going to be wrapping the plus of their data. But remember now, because data is the actual numbered Python number, so this operator here is just the typical floating point plus addition now. It's not an addition of value objects, and will return a new value. So now a plus b should work, and it should print value of -1. because that's 2 plus minus 3. There we go. Okay, let's now implement multiply, just so we can recreate this expression here. So multiply, I think it won't surprise you.
Okay, I wouldn't do this myself, but I need the syntax. Maybe it was mentioned somewhere. What is the dunder method for multiplication? I just need the syntax. Mul, okay. I could have probably guessed that, whatever. Def mul self other output equals value self dot data times other dot data return output. Is this correct?
Will be fairly similar. So instead of add, we're going to be using mul, and then here, of course, we want to do times. And so now we can.
Okay, so let's test it. -6. Yes, sir.
Create a C value object, which will be 10.0. And now we should be able to do A times B. Well, let's just do A times B first. That's value of -6 now. And by the way, I skipped over this a little bit. Suppose that I didn't have the repr function here. Then it's just that you'll get some kind of an ugly expression. So what repr is doing is it's providing us a way to print out like a nicer looking expression in Python. So we don't just have something.
Yeah, this is basically like the object. Yeah, that's nasty. That's ugly.
Cryptic. We actually are, it's value of -6. So this gives us a times, and then this we should now be able to add C to it because we've defined and told the Python how to do.
Let me do that. C equals value 10.0 A times B plus C. So again, this is the same, literally same equation.
Do mul and add, and so this will basically be equivalent to A dot mul of B, and then this new value object will be dot add of C. And so let's see if that worked. Yep, so that worked well. That gave us 4, which is what we expect from bit 4. And I believe we can just call them manually as well. There we go. So
whoa. This is cool, calling it manually. A with an object dot, and we access the function mul of that object. We pass the B as a parameter, and then on that we access. Oh my god, this is nice. This is nice. I want to do it. Okay, let's comment this out. Also, I need to step up my keyboard shortcut speed because Andrej Karpathy is actually embarrassing me. So, I mean, whatever. A dot underscore mul B. Wait, do we need? Yeah, it needs to be in a wrapped like this. Dot and then add C. Beautiful. Okay, I need to learn this keyboard shortcut, man. What is the keyboard shortcut for Google Colab that instantly comments out the current line? I'm using really control backlash. Oh my god. I mean, I know this from like highlighting multiple lines and commenting down, but I didn't realize that you can just be anywhere in the line. Man, I'm such a noob. Oh my god, this is so disgusting.
Yeah. Okay, so now what we are missing is the connective tissue of this expression. As I mentioned, we want to keep the.
Here we save as a D. A little sneaky. So we don't need this in D.
These expression graphs. So we need to know and keep pointers about what values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children.
Well, what?
And by default, it will be an empty tuple. And then we're actually going to keep
children.
A slightly different variable in the class, which we'll call _prev, which will be the set of children. This is how I did it in the original Micrograd, looking at my code here. I can't remember exactly the reason. I believe it was efficiency, but this
Okay, that's kind of funny.
This underscore children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set, I believe for efficiency. So now when we are creating a value like
this, I'm not too clear about. Maybe he'll explain it, so I don't want to like, you know, panic. So this is empty tuple. Interesting. So we just get turn the tuple into a set. Very curious. Sure.
This with a constructor, children will be empty and prev will be the empty set. But when we're creating a value through addition or multiplication...
Okay, I actually, you know, I need to refresh my knowledge on data types. Explain the differences between tuples and sets in Python. Use simple terms. Okay, I need to probably change my custom instructions, to be honest. Oh, incognito. Wow, I didn't even know Perplexity had this feature. But I need to change my custom instructions because this is answering too concisely. When explaining new concepts to the user, be thorough and focus on the fundamentals. Okay, maybe I'll get better outputs now. Explain between tuples, sets, lists, and dictionaries in Python. Use simple terms. Lists, ordered, changeable, allow duplicates, use square brackets. Tuples are still ordered but are unchangeable. They do allow for duplicates and use parentheses, but they're unchangeable. So that's the main difference. Sets, unordered, unchangeable, no duplicates. Why is it curly brackets the same as dictionaries? What the heck? Interesting. This is a fast way to search stuff. Ask follow-up. And Perplexity is like so many cool features that are not obvious. Okay, sets, unordered. So basically set is the most efficient way to store something because it's no duplicates and it's unordered and unchangeable. Okay.
Going to feed in the children of this value, which in this case is self and other.
Wait, what?
Set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self and other.
One more time, please.
See. So now when we are creating a value like this with a constructor, children will be empty and prev will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self.
One more thing I want to change is that why didn't this save? Why didn't this save? Okay, I need to delete this. When explaining new concepts, always be thorough, focusing on the fundamentals. Use simple and easy to understand language when explaining things. Do I have to hit save somewhere? Oh yeah, here. That makes more sense. So now if I do the same prompt, explain between tuples, lists, and sets In Python, it should be more thorough explanation, not as concise, right? Yeah. Yeah, my custom instructions were way too aggressive. Lists are the most common and versatile sequence in Python. Yep. Mutable, you can add, remove, or change elements after creation. Ordered, elements maintain their order. Allow duplicates. Use lists when you need a collection of items that might change over time. Tuples. Tuples are similar to lists, but with one key difference. They are immutable. Once created, you can't change, add, or remove elements. Ordered. Maintain their order, allow duplicates. Use tuples for collections that shouldn't change, like coordinates or RGB color values. Sets. Sets are quite different from lists and tuples. Okay, mutable, you can add or remove. You can add or remove elements after creation. Unordered. This is the main key, I think. Maybe I'll link this doc below the video with the key learnings. I can also link my Google Colab.
Another, I believe, for efficiency. So now, when we are creating a value like this with a constructor, children will be empty and prev will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self and other. So those are the children.
Okay, I'm getting confused, which is bad. Children of this value.
So now, when it will be a tuple for convenience, this is how it will be an O and keep pointers about.
Okay, I need to understand this part.
What values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children, and by default it will be an empty tuple. And then we're actually going to keep a slightly different variable of b, and then this new value object will be dot add of c. And so let's see if that worked. Yep, so that worked well. That gave us 4, which is what we expect from before. And I believe we can just call them manually as well. There we go. So yeah. Okay, so now what we are missing is the connective tissue of this expression. As I mentioned, we want to keep these expression graphs, so we need to know and keep pointers about what values produce what other values. So here, for example, we are
okay, this is helpful because now I remind myself of what we're doing. If we remember at the very beginning of the video, we want to see like when we have, you know, let's say G, how we got through it, you know, F, E, D, C, A, B. So this we haven't built into the value class. We need to make sure that these objects can do this. So that's what we're making now. So okay, this was the missing context that I
to introduce a new variable, which we'll call children, and by default it will be an empty tuple. And then we're actually going to keep a slightly different variable in the class, which we'll call underscore prev, which will be the set of children. This is how I did it in the original.
Okay, so since what we've learned about the tuples and sets, tuple will be likely all children leading up to that object, but a set has to have only unique stuff in it. So self.prev is a set of children. So it will extract all the unique values that were required to make this object. But there could be like multiple, you know, of the same ones, which will be stored in the children tuple. But for the set, we only keep unique ones. If you look into our notes, use sets when you need to ensure uniqueness of elements. So all of the elements in a set will be unique, but in the tuple, we can have copies. So I guess that's why we're having both a tuple and a set.
Micrograd, looking at my code here, I can't remember exactly the reason. I believe it was efficiency, but this underscore children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set, I believe for efficiency. So now, when we are creating a value like this with a constructor, children will be empty and prev will be the empty set. But when we're creating a value through addition or multiplication, we're going.
Now we need to work with the values because they're still empty. Okay, so I'm catching back on, you know. When we initialize, it's empty. But if we're like adding up, we need to store what we added up. into these two data sets, data
to
types.
feed in the children of this value, which in this case is self and other. So those are the children. Addition or multiplication, we're going to feed in the children of this value, which in this case is self and other.
Yes, okay. I don't know why that was confusing, but yeah, now it makes perfect sense. So value equals self data plus other data, and then interesting. Self other. So this is the tuple going into here. Self is obviously not okay, so this is the data. So we're using this function. I don't know why I'm even I don't know what I'm doing. Why am I looking here? When we're adding, we call self and other. And that would be just this. And this is the output. I don't know why I'm trying to... Oh yeah, value. Okay, so I should be looking here. Man, why am I running in circles here? The output is setting a new object of the value class. So I should be looking at initialize. Self is skipped, and then data is this, and then the tuple is this. Okay, yeah.
So those are the children here. So now we can do d.prev, and we'll see that the children of the, we now know, are this a value of negative 6. So now we can do d.prev, and we'll see
d.prev. Interesting. No, only a single one, prev. So we have 4 is the result, yeah? That hasn't changed, but we stored the children into our set. And we have -6 and 10.
See that the children of the, we now know, are this a value of -6 and value of 10. And this, of course, is the value resulting from A times B and the C value, which is 10. Now, the last piece of information we don't know, so we know now the children of every single value, but we don't know what operation created this value. So we need one more element here. Let's call it _up. And by default, this is the empty set for leaves. And then
empty set? Empty string? I think that's how you declare an empty string, but it wasn't said like this. Same as dictionary. Whatever.
and we'll just maintain it here. And now the operation.
I want to ask, like, you know, I'm going to give it this code. Ask, why, like, when and why are variables named with underscore in Python programming in general? Variables named with a leading underscore in Python programming in general serve specific purposes, follow certain conventions. Here is a simple explanation. Single leading underscore, when to use, for internal use within a module or a class, to indicate that a variable or method is meant to be private, though not strictly enforced in Python. Why? It's a naming convention that tells other programmers This is intended for internal use. Please don't use it directly outside this class or module. Okay. Again, I feel like I should know this. Maybe it's like some of the things I know intuitively, but not explicitly.
Will be
Yeah, maybe this is what I can add. You know, add these beginner comments that you know, Andrej just skips because he knows it, but for me it's super valuable.
just a simple string, and in the case of addition, it's plus. In the case of multiplication, it's times.
Whoa, what?
And now the operation will be just a simple string, and in the case of addition,
Wait, it is a
it's
string.
plus.
He said set.
In the case of multiplication, it's times.
Okay.
So now we not just have d.pref, we also have a d.op. And we know that d was produced by an addition of those two values. And so now we have
Oh. So d a times b, and then this is the first one, and then you have of minus 6 d dot op. Oh, I need to run this. If I don't run it, then it doesn't exist. Never mind. Yeah, but it doesn't know that the left side of the equation, I mean, this, it doesn't know that a times b, it only knows like the product of this and this. Because like this is minus 6 and 10, but it doesn't know that it's 2 times minus 3, or does it? I don't know.
the full mathematical expression, and we're building out this data structure, and we know exactly how each value came to be, by what expression, and from what other values.
Okay,
Now,
why not just ask Claude, right? In the code above, we can, when we run d.pref, we can get the values that created d. However, that will return, that will only return, but does it know that minus 6 was created with 2 times minus 3 or not? Take a deep breath and let's work through this in a step-by-step way. Let's analyze the code and the behavior of the pref attribute step by step. Understand the value class. The value class is designed to present a value and keep track of its operations. Okay, when we access d.prev, we get -6 and 10. This shows the immediate previous values used to create d. Tracking the operation. The op attribute of d stores the operation used to create it, which is plus in this case. Now, to answer your question, does it know that -6 was created with 2 times -3? The answer is yes and no. Perplexity, come on. Direct knowledge. D itself doesn't directly know that -6 was created with 2 -3. It only knows its immediate previous, or maybe it's stored in the object. Oh. D.prev, and then if we access the first value, can we do that? D.prev 0, I mean this will probably throw an error, that underscore prev. Yeah, the object is not subscriptable, but maybe, oh no, wait, d.prev makes no sense. Anyways, I think maybe if we had like one of the standard methods, I think there was one for accessing a list, but I'm not sure if it's applicable here. Okay, it only knows its immediate previous values and the operation used to create it. Indirect knowledge, however, the information is not lost. The value object with data -6, let's call it temp, does know it was created by multiplying 2 and -3. This information is stored in temp.prev and temp.op. So we would have to like store this as a, maybe we can access it somehow, I don't know. Recursive checking. To get the full history of the operation, you would need to recursively traverse the prev sets of each value object. Okay. Ask follow-up. In conclusion, get the full history of operation for value. You will need to indeed recursively. Here's how you could implement this. So I have to do a history list. Yeah, okay. But yeah, it is stored, but not easily accessible right now.
Because these expressions are about to get quite a bit larger, we'd like a way to nicely visualize these expressions that we're building.
Okay, so I guess we're building that now. I'm really getting ahead of myself.
So for that, I'm going to copy-paste a bunch of slightly scary code that's going to visualize these expression graphs for us. So here's the...
Okay, so let's see how different this is from what Claude 3.5 cooked up. Seems like Karpathy's code is a bit more advanced, as expected. I mean, if, Claude 3.5 Sonnet was the coding level of Andrej Karpathy, eesh, that would be crazy. But we just pasted a lot of code, so let's see.
The code, and I'll explain it in a bit. But first, let me just show you what this code does.
Okay, so let's, I guess, write it out then. From graph with import digraph. Graph. Should I split screen this? Graph with import digraph. We have trace. We define a new function trace with root as the parameter. Builds a set of all nodes and edges in a graph. Nodes, edges equals set. Set two empty sets. Okay. New function build with v. If v not in nodes, so if v is not in nodes, if it doesn't exist in the nodes set, nodes dot add v. For child in v dot prev, is there a wait, am I missing something? Is it declared that v is a value object? Maybe not, but maybe we don't need to do that just yet. I don't know. Edges.add child v as a tuple. Build child. Build root. Okay, I really need Andrej to explain this. I'm gonna be honest. Okay, let's do another function, def draw dot. And I know I could just copy paste this code, but again, I want to write it out because I want to actually learn this and understand this. Maybe I should probably play the explanation first.
Basically what it does is it creates a new function draw dot that we can call on some root node, and then it's going to visualize it. So if we call draw dot on D, which is this final value here, that is a times b plus c, it creates something like this.
Wow.
So this is D, and you see that this is a times b,
Very nice.
creating an intermediate value plus c gives us this output node D. So that's draw dot of D.
Beautiful.
And I'm not going to go through this in complete detail. You can take a look at Graphviz and its API. Graphviz is an open source graph visualization software. And what we're doing here is we're building out this graph in Graphviz API.
Okay, so I guess if we're not getting a detailed explanation, let me quickly write it out. Dot digraph format equals SVG. You could actually have this in Claude artifacts. Rank dir LR. And I'm running out of light. Left to right, okay. Nodes edges equals trace root for n in nodes. UID equal, I guess it's the user ID or something. String ID n for any value in the graph. Create a rectangular record node for it. Dot that node. Name equals UID. Label equals data modulo 4f. I kind of wish Karpathy explained everything, because this is getting pretty crazy. If and that op, if this value is the result of some operation, create an op node for it. Dot that node name equals. I mean, this should not be that complex. Like, we're not writing a new kernel in assembly, but like, maybe my skills really are rusty after all. Name equals UID plus n.op. Label equals n.op. And connect this node to it. Dot that edge UID plus n.op UID. For n1 and 2 in edges. Connect n1 to the OP node of n2. Dot that edge str id n1 str id n2 plus n2 dot op. return dot. Hopefully this is correct. If not, then I'm just bad. But what we can do is actually take this as a screenshot, put it here, and then does the code, okay, on the screenshot match the code above exactly. What? The screenshot uses v.pref while your code uses v.pref? In the trace function? What do you mean? Am I crazy or is this the same? Draw.function, the screenshot has a comment which is not present in your code. Sure. Except that it is. What the you literally look at what you just wrote. Most of these are exact matches. Anyways, we'll see when they run it, I guess.
And
or wait, maybe. Oh yeah, he has it here. First half. And we can do like text compare. Use one of these sites. I don't know why it doesn't work. Oh my lord, okay. So let's compare it. This is Karpathy's, and this is what I just wrote. Compare. What is different? Oh, okay. Wait, what? I mean, this should be one more left. Okay, so. Oh, there's a comma that shouldn't be here. Oops. Yeah, I mean, when writing so much stuff manually, there's a comment. Comment difference. What is different here? Dot node name UID. Oh, this is not in the code. Whatever, let's play it out. We'll see if our code works or not.
you can basically see that trace is this helper function that enumerates all of the nodes and edges in the graph. So that just builds a set of all the nodes and edges. And then we iterate through all the nodes in the graph.
Maybe we just do like this. Transcribe the code from the screenshot exactly, then correct any errors you made. Oh, let's not include this. Now compare it to this code and list out all the differences. Essentially identical. Formatting and white space. Indentation. The image uses 2-space indentation, 4-space indentation. Purely cosmetic. Okay, good.
So that just builds a set of all the nodes and edges. And then we iterate through all the nodes and we create special node objects for them in using dot node. And then we also create edges using dot.edge. And the only thing that's like slightly tricky here is you'll notice that I basically add these fake nodes, which are these operation nodes. So for example, this node here is just like a plus node. And I create these special op nodes here, and I connect them accordingly. So these nodes, of course, are not actual nodes in the original graph. They're not actually a value object. The only value objects here are the things in squares. Those are actual value objects or representations thereof. And these op nodes are just created in this draw.routine so that it looks nice.
Yeah.
Let's also add labels to these graphs just so we know what variables are where.
Why not?
So let's create a special underscore label, or let's just do label equals empty by default.
So from what we've learned, the fact that he didn't go underscore means that it should be exposed outside of the class. Probably, I don't know, we'll see. Okay, let's scroll back up. Label equals empty string. I don't know why he does the single quotation marks. I'm used to doing double. I don't know, doesn't matter, I think.
And save it in each node.
It was sweet to run it after each change.
And then here, we're going to do label is A, label is B, label is C, and then...
Okay, let's do that. Literally copy this for speed.
Let's create a special E equals A times B, and E dot label will be E.
So that would be like the temp, you know, when I had Perplexity explain it. In this case, he declared it as an E variable. But yeah, E equals A times B. Wait, using this semicolon in Python. Wait a second, isn't that like sacrilegious? I need this confirmed. Why would someone use the semicolon in Python? I mean, I suspect how it works, so let's just ask why, and I mean, and in what instances would this be used? It's relatively uncommon, but it does have specific use cases. Statement separation. Yes, multiple statements on a single line. Yeah, I mean, so obviously, like in C# this is standard, but in Python you don't use it. But I guess he really wanted to have these on a single line. So, yeah.
It's kind of naughty. And E will be E plus will be E. It's kind of naughty. And E will
yes,
be...
it doesn't seem like the most elegant solution, but who am I to critique Karpathy?
E plus C. And a D dot label will be D.
Okay.
Okay, so nothing really changes. I just added this new E function, new E variable. And then here, when we are printing this, I'm going to print the label here. So this will be a %s bar, and this will be n.label.
Okay, this is crazy. %s in the string. Is it just a string? I don't know, maybe this is syntax of the graph with. Yeah, I don't know. This is completely outside of my realm of competence. But let's just go. Data, and what else did you do?
Here. So this will be a %s bar, and this will be n.label.
N.label.
And so now
What is the... There has to be a keyboard shortcut for this. What is the Google Colab keyboard shortcut to run all changed boxes? I don't want to run every single box of code in my notebook, just the one I recently changed. Surely there is one for this. Control F9? Really? Run all. Control F9. Okay, I guess we'll try it. So let's see. Let's do like a comment here. Test. Random comment here. Test. And then Control F9 should only run these two. Seems to be working. Anyways, let's remove this. But it does seem to run the entire notebook though. I don't know.
We have the label.
Wait. Oh, draw dot. Okay, I didn't do that. I was like, why am I not sure? Draw dot D. Oh, definitely not minus. Draw dot D. Boom. Almost the same. For us, it's going up. Is that coincidence? Why is it for him going down and for us going up? I mean, it doesn't really matter, but you know. Okay, whatever.
On the left here. So it says A, B creating E, and then E plus C creates D, just like we have it here. And finally, let's make this expression just one layer deeper. So D will not be the final output node. Instead, after D, we are going to create a new value object called F. We're going to start running out of variables soon. F will be negative 2.0.
Okay, let's see. What are we cooking now? F. Value object of negative 2.0.
And its label will, of course, just be F.
Couldn't this be automated? Like, you know, what I mean by that is just automatically assign the label to the name of the variable. Surely Python can do that. Whatever. Let's follow. Let's not question Karpathy.
And then L, capital L, will be the output of our graph. And
Capital
L will be D times F. Okay?
Let's
So
take
L
the
will be
capital
negative
L
8 is the output.
equals D times F, then capital L.
Okay, so L will be negative 8 is the output. So now we don't just draw a D, we draw L.
Let's draw this L. Okay. A and B created E, C and E created D, and D and F created L, but the L is not written there.
Okay. And somehow the label of L was undefined. Oops.
Yeah. Okay, beautiful.
Well, that label has to be explicitly sort of given to it. There we go. So L is the output. So let's quickly recap what we've done so far. We are able to build out mathematical expressions using only plus and times so far. They are scalar valued along the way, And we can do this forward pass and build out a mathematical expression. So we have multiple inputs here, A, B, C, and F, going into a mathematical expression that produces a single output, L. And this here is visualizing the forward pass.
Yeah, so this
So
is
the output of the
only for
forward pass-
visualization. Like this only to visualize what the forward pass looks like. Doesn't like do anything, just like only to get this graph. It's important because this is the code I understand the least.
Pass is -8. That's the value. Now, what we'd like to do next is we'd like to run backpropagation. And in backpropagation, we are going to start here at the end, and we're going to reverse and calculate the gradient along all these intermediate values. And really what we're computing for every single value here, we're going to compute the derivative of that node with respect to L. So the derivative of L with respect to L is just 1. And then we're going to derive, what is the derivative of L with respect to F?
Whoa. Slow down. Let's load up our document over here. Derivative shows the rate of change or slope of a function at any given point, used to find a maximum minimum value. Okay, but surely this isn't all, like we're using it in a different way. What are the most common way the math concept of is used in ML/AI? Explain, or just in math in general. Explain in simple terms. Derivatives are a fundamental concept in calculus that have several important applications in machine learning, AI, and mathematics in general. Here are some of the most common ways derivatives are used, explained in simple terms. Optimization in machine learning. Derivatives are crucial for optimization algorithms like gradient descent, which are used to right now, backpropagation, we're doing that, but like machine learning models, the derivative tells us which direction to adjust the model's parameters to minimize error and maximize performance. It's like using in neural networks, derivatives are used in the backpropagation algorithm to calculate how much each weight. We needed this. In neural networks, derivatives are used in the backpropagation algorithm to calculate how much each weight in the network contributes to the overall error. This allows the network to learn and improve its performance over time. Function approximation. Derivatives help in approximating complex functions with simpler ones. This is useful in many areas of machine learning and mathematics. Okay, we also need this. Rate of change analysis. In general mathematics and science, derivatives are used to analyze how quickly a quantity is changing. For example, velocity is the derivative of a position with respect to time. Okay. Perfecting. We don't need this.
Intermediate values. And really what we're computing for every single start here at the end, and we're going to reverse and calculate the gradient along all these intermediate values. And really what we're computing for every single value here, we're going to compute the derivative of that node with respect to L. So the derivative of L with respect to L is just 1. And then we're going to derive, what is the derivative of L with respect to F, with respect to D, with respect to C, with respect to E, with respect to B, and with respect to A. And in a neural network setting, you'd be very interested in the derivative of basically this loss function, L, with respect to the weights of a neural network. And here, of course, we have just these variables A, B, C, and F, but some of these will eventually represent the weights of a neural net. And so we'll need to know how those weights are impacting the loss function. So we'll be interested basically in the derivative of the output with respect to some of its leaf nodes. And those leaf nodes will be the weights of the neural net. And the other leaf nodes, of course, will be the data itself. But usually we will not want or use the derivative of the loss function with respect to data because the data is fixed, but the weights will be iterated on using the gradient information. So next we are going to create a variable inside the value class that maintains the derivative of L with respect to that value. And we will call this variable.
Okay, so now it's getting interesting. The first 30 minutes were kind of easy, manageable. I wouldn't say easy, but manageable, right? Now that we're like going deep into calculus concepts and the functions are getting longer and longer, you're gonna really have to pay attention to keep up.
So there's a dot data and there's a self.grad, and initially it will be 0. And remember,
that is self.grad is for the gradient.
Remember that 0 is basically means no effect. So at initialization, we're assuming that every value does not affect the output, right? Because if the gradient is 0, that means that changing this variable is not changing the loss function. So by default, we assume that the gradient is 0. And then now that we have grad and it's 0.0.
Of course, floating point.
We are going to be able to visualize it here after data.
Okay, Control F9.
So here grad is 0.4.
Whoa. Here, after data.
And this will be in that grad. So here grad is 0.4f.
I need this explained. I'm going to ask Perplexity.
And this will be in that grad.
And dot grad. I need this explained. I need the above code explained, particularly this piece. And let's put this inside. Let's do the entire line of code, I guess. This line. Certainly, let's break down this line of code and explain its purpose within the context of visualizing a computational graph. This line is creating a node in the graph viz visualization. Here's what each part means. .node, this is a method call to create a node, a new node in the graph, okay? Name equals UID. This sets the unique identifier for the node, UID. It's created earlier in the function as UID equals string of IDN, which converts the Python's object unique ID. Python object's unique ID to a string. Okay. This is built-in Python function. Label equals, this defines the label that will be displayed in the node. It's using a format string with placeholders. Oh, okay. Why didn't I just read the name of the variable? So these are the separators, like the hard walls, I guess. And this is the formatting, the graph viz. Using a format string with placeholders. %s will be replaced by n.label. Oh wow. So this is like the placeholder. Why would okay, what's the point of doing this then? Why not just do it directly? Oh, because we can I guess this is the easy way. Rather than using a complex f strings, this is the more manageable way where you just do placeholder as the percentage and then do n.label and .data. And 4f is 4 decimal points in a float. Ah, okay. Alright. Now we're getting there.
And now we are going to be showing both the data and the grad.
Okay, let's run it. We need to do Control F9 again. Yes, we have the grad. It's 0 everywhere though.
Initialized at 0. And we are just about getting ready to calculate the backpropagation. And of course, this grad, again, as I mentioned, is representing the derivative of the output, in this case L, with respect to this value. So with respect to, so this is the derivative of L with respect to F, with respect to D, and so on. So let's now fill in those gradients and actually do backpropagation manually. So let's start filling in these gradients and start all the way at the end, as I mentioned here. First, we are interested to fill in this gradient.
There should be 1.
So what is the derivative of L with respect to L? In other words, if I change L by a tiny amount h, how much does L change? It changes by h. So it's proportional, and therefore the derivative will be 1. We can, of course, measure these or estimate these numerical gradients numerically, just like we've seen before. So if I take this expression and I create a def LOL function here and put this here. Now, the reason I'm creating a gating function LOL here is because I don't want to pollute or mess up the global scope here. This is just kind of like a little staging area. And as you know, in Python, all of these will be local variables to this function. So I'm not changing any of the global scope here. So here, L1 will be L.
Let's do that. Copy all these. Control and B. Oh, definitely not here though. Here. Do we have any? No. No parameters. Boom. L1 equals L. L1 equals L. Okay. Interesting.
And then copy pasting this expression, we're going to add a small amount h in, for example, A.
Okay. H equals 0.0001. And then we copy this. Plus H.
Right? And this would be measuring the derivative of L with respect to A. So here, this will be L2. And then we want to print that derivative. So print L2 minus...
Wait, we already did this. Print L2 minus L1 divided by H. Correct? Oh, we don't... We need to run it on something.
minus L1, which is how much L changed, and then normalize it by H. So this is the rise over run. And we have to be careful because L is a value node, so we actually want its data.
Okay, dude. L.data. L.data. Yeah, because we would have to define subtraction the same way we define the other Dunder methods, right? At least that's my intuition. We have for addition, but we don't have subtraction. So yeah. 6. Small change.
So that these are floats dividing by H. And this should print the derivative of L with respect to A, because A is the one that we bumped a little bit by H. So what is the derivative of L with respect to A? It's 6. Okay, and obviously, if we change L by H, then that would be here effectively. This looks really awkward, but changing L by H, you see the derivative here is 1. That's kind of like the base case of what we are doing here. So basically we can come up here and we can manually set L.grad to 1. This is our manual backpropagation.
Okay, I need the keyboard shortcut for inserting the coding above.
And we can off what we are doing here. So basically we can come up here.
Control MA. Okay, so Control MA, Control MB, Control MA, yeah.
So basically we can come up here and we can manually set L.grad to 1. This is our manual backpropagation. L.grad is 1, and let's redraw. And we'll see that we filled in grad is 1 for L. We're now going to continue the backpropagation. So let's here look at the derivatives of L with respect to D and F. Let's do D first. So what we are interested in, if I create a markdown
Let's use our new keyboard shortcut, Control MA.
Here, is we'd like to know, basically we have that L is D times F.
L is D times F, correct.
And we'd like to know what is dl by dd. What is that? And if you know your calculus, L is D times F, so what is dl?
To the power of 2 times df. Is for this side. Let's see.
L by dd, it would be F. And if
okay, I'm completely fucking... oh, derivative. Oh my god, I'm confused with the D, because, you know, that's for derivative of L divided by derivative. Yeah, whatever.
If you don't believe me, we can also just derive it, because the proof would be fairly straightforward. We go to the definition of the derivative.
You know what, let me have it explained. The second line, dl divided by represents a derivative in calculus. In simple terms, it's asking about the rate of change of L with respect to D. And whether that, yeah, but I need to know, like, D stands for derivative, whether that rate of change is equal to F. I mean, yeah, when you explain it like this, it's obvious, but this notation is not obvious. In simple, asking of the rate of change of L with respect to D. I mean, yeah, that's F. We have a simple equation. dl dd is a notation for the derivative of L with respect to D.
Which is f of x plus h minus f of x divide h. As a limit
Slow it down.
L is D times F, so what is dl by dd? It would be F. And if you don't believe me, we can also just derive it, because the proof would be fairly straightforward. We go to the definition of the derivative, which is f of x plus h minus f of x divide h. As a limit of h goes to 0 of this kind of expression. So when we have L is D times F, then increasing D by H would give us the output of D plus H times F. That's basically f of x plus h, right? Minus D times F. And then divide H. And symbolically expanding out here, we would have basically D times F plus H times F minus D times F divide H. And
oh, so this is nice. So we're just doing like basic algebra, like breaking it down. I don't know, like this was probably my favorite part of math, like breaking something into simpler terms and finding the simplest representation. So like D times F plus H times F minus. Okay, let's see.
then you see how the df minus df cancels.
Yeah, that cancels out, and then H times, yeah, H times F divided by H. I mean, you can just cancel those out and it's F.
So you're left with
beautiful.
H times F, divide H, which is F. So in the limit as H goes to 0 of, you know, derivative definition, we just get F in the case of D times F. So symmetrically, dl by df will just be D. So what we have is that f dot grad, we see now, is just the value of D, which is 4. And we see that...
Wait, so why are we setting it manually though?
So symmetrically, dl by df will just be D. So what we have is that f dot grad, we see now, is just the value of D, which is 4.
I'm not sure why we're doing that manually. F dot grad. 4.
And we see that d dot grad is just the value of f. And so the value of f is -2.
You know, it's funny because I just literally listened to Andrej Karpathy's keynote about 10,000 hours and why he's such a believer in this rule. I mean, if you're not familiar, the concept of 10,000 hours is it takes around 10,000 hours to become an expert in something, right? Obviously, even more to become world class, like Andrej Karpathy probably has like 30, 40,000 hours in AI at least. But it takes at least 10,000 hours to, you know, master something, to develop mastery. So what he said is that you should just focus on getting there. Now, if you're doing something for 6 hours a day, it will take you roughly 5 years. If you can do it for 10 hours a day, it will take you 3 years. Now, you know, the 6 hours a day is more manageable, especially if you have a full-time job. But like, that's kind of inspirational. Because like, even with 6 hours a day, you can do that with a full-time job, on top of a full-time job. And in 5 years, you will be a master at something. So if this is like, you know, if your head is spinning, just focus on putting in the hours. Like, obviously it depends what your goal is, but like, what he said is that you have to learn how your dopamine system works. And what that means is basically how your brain gets reward. And breaking that even to simpler is like what gives you inspiration and energy. And you have to make sure that you basically can get to the 10,000 hours by doing the 6 hours a day. So like working on interesting projects, right? That was one of his tips. But like, you have to figure out that for yourself. What you have to do to get to the 6 focused hours a day, every day, you know, maybe starting a new business or whatever your goal is. And then just make sure that you don't lose interest and don't give up, and just track the hours. Literally track the hours you put in. And, you know, don't be surprised that you don't see any results in the first few hundred hours. You're gonna see like obviously you're gonna have the most learning at the start, but once you reach mastery, you'll be able to do projects like this, you know, on the weekend. And something like, if I had to build this from scratch, not having any tutorials or even AI coding tools, it could take me multiple months, right? Maybe even longer, I don't know. But Karpathy can just do it on a weekend because he has those 10,000 hours. So just a quick anecdote there.
2. So we'll set those manually. Let me erase this markdown node, and then let's redraw what we have is -2. So we'll set those manually.
Oh, he didn't do negative minus.
Let me erase this markdown.
Oh my god, isn't that
node,
legal?
And then let's redraw what we have.
Wait, he deleted it. What? Okay, I need the keyboard shortcut for that. What is the Google Colab keyboard shortcut for deleting the current cell? Control MD, okay. Well, I guess we run this, and then we delete it. And then we delete this as well. And we redraw this. And we see we have the correct gradient.
Okay, and let's just make sure that these were correct. So we seem to think that dl by dd is -2, so let's double check. Let me erase this plus h from before. And now we want the derivative with respect to f.
Let's erase this as well.
So let's just come here when I create f, and let's do a plus h here. And this should print the derivative of L with respect to f, so we expect to see 4.
Plus h. Okay, I'm kind of getting lost in the numbers. I mean, not lost, but like my neural connection isn't as strong with what we just did with this. Like, to me, I like compartmentalize it, whatever, that we done it before, but it's still the current thing. F value -2, which is f plus h, but we set h as 0.01. Okay. L1 plus L2. Why though? Why? Why is it 4 here now? With 0.01. We didn't redraw it. Why is 4 L2 minus L1? Wait, what if I remove it? 0. I don't know.
Yeah, and this is 4 up to floating point funkiness. And then dl by dd should be f. And now we want the derivative with respect to f. So let's just come here when I create f, and let's do a plus h here. And this should print the derivative of...
But why? It's 0.01.
of L with respect to f, so we expect to see 4.
But this is just an arbitrary small number to... That way it's not 0. Seems like. How f changes.
With respect to f, to think that dl by dd is -2, so let's double check. Let me erase this plus h from before. And now we want the derivative with respect to f. So let's just come here when I create f, and let's do a plus h here. And this should print the derivative of L with respect to f, so we expect to see 4. Yeah, and this is 4 up to floating point funkiness. And then dl by dd should be f, which is -2. Grad is -2. So if we, again, come here and we change d dot data plus equals h right here. So we expect, so we've added a little h, and then we see how L changed, and we expect to print -2. There we go.
Yeah. I mean, I don't want to get stuck here, but you know, for me, I would literally have to remind myself of this, because it's been like at least 3.5 years since I've done any serious math on this level, and I just don't wanna... I mean, it's not even a high level of math. The point is just like my context window is not loaded with this stuff, right? So that's why I need to remind myself every literally few minutes. But yeah, we still need to keep going. Because like, I do understand what's happening, but not on a like fundamental level, not on a, you know, instantly seeing it level. Man.
So we've numerically verified. What we're doing here is kind of like an inline gradient check. Gradient check is when we are deriving this like backpropagation and getting the derivative with respect to all the intermediate results. And then numerical gradient is just, you know, estimating it using small step size. Now we're getting to the crux of backpropagation. So this will be the most important node to understand, because if you understand the gradient for this node...
Okay, let's try to understand this previously, right? It's 0, okay. Without this little piece, it's 0. If we're setting a new object that's completely separate from the previous ones, it's you know, defined from 0. Defining new object is -2 with the label f. And then L, which is, I guess, a loss function in this case, d times f, L dot data. So L2 minus L1 divided by h. So L1, okay, L2 is d times f, and in this case f is, I need to use comments, right? In this case f, if we add the h, basically minus 1.999, and then okay, d E is a times b, so d is minus 4 again. Minus 4. Okay, 2 minus 3, 10. And this is a times b, so this is minus 6. And then we add 10. So this is 4. Wait, 4. A times b minus 6. We add 10. It's 4. So here we're at minus 101. This is gonna be, 4 times minus 101. But here, this is minus 2. It's still 4. So here it's exactly minus 8. But here it's not. So minus 8. So let's just run this calculation. This is the result. Would have calculated that in my head, but whatever. So now we just do L2 divided by L1 divided by H. So what this looks like is 7.996 minus minus is plus, so 8.000 has to be like this, divided by 0.001. So this is, basically 0.004 divided by 0.001, which is 4. But what I don't understand is why this gives us 4, right? Because like before we were not using 001. What if I just do 2 here? Like it completely messes it up, no? No, it doesn't. That's crazy. Oh, wait. Oh, because we divide it. So then the two equations, isn't it literally the same as we had before? But that's what I mean, like it's not complex thing. I just like, it's not like really internalized for me. Okay, if it's 0.002, and this is 8, and this is like 2, so this is 8 divided by 2. Wow, so it stays the same. So it really shows you the difference. But what I don't understand is like how the H just like makes that happen, and without it, it's not visible at all. Some small change. I guess you need to apply some small change to the value. I don't know. Let's continue.
So we've added a little h, and then we see how L changes. And then dl by dd back to f, so we expect to see 4. Yeah, and this is 4 up to floating point funkiness. And then dl by dd should be f, which is -2. Grad is -2. So if we again come here and we change d dot data plus equals h.
Two.
Right here. So we've added a little h, and then we see how L changed, and we expect to print -2.
Wait. It didn't print negative 2 for me. Did I mess something up? It printed positive 2. What is going on? Oh my god, I kept this in.
There we go. So we've numerically verified. What we're doing here is kind of like an inline gradient check. Gradient check is when we are deriving this like backpropagation and getting the derivative with respect to all the intermediate results. And then numerical gradient is just, estimating it using small step size. Now we're getting to the crux of backpropagation. So this will be the most important node to understand, because if you understand the gradient for this node, you understand all of backpropagation and all of training of neural nets, basically. So we need to derive dl by...
That's a strong promise.
Estimating it using small step size. Now we're getting to the crux of backpropagation. So this will be the most important node to understand, because if you understand the gradient for this node, you understand all of backpropagation and all of training of neural nets, basically. So we need to derive dl by dc. In other words, the derivative of L with respect to C.
Why is C the most important data point here?
Because we've computed all these other gradients already. Now we're coming here and we're continuing the backpropagation manually. So we want dl by dc, and then we'll also derive dl by de. Now here's the problem. How do we derive dl by dc?
You tell me.
We actually know the derivative L with respect to d, so we know how L is sensitive to d. But how is L sensitive to c? So if we wiggle c, how does that
Just derivative of d.
Impact L through d? So we know dl by dc, and we also here know how c impacts d. And so just very intuitively, if you know the impact that c is having on d and the impact that d is having on L, then you should be able to somehow put that information together to figure out how C impacts L.
Oh, okay. So we know that C is influenced by E. So that's -6 impact on D, and D has -2 impact. So is that +12 then? Yes, +12
and
impact.
Indeed, this is what we can actually do. So in particular, we know, just concentrating on D first, let's look at what is the derivative basically of D with respect to C. So in other words, what is dd by dc? So here we know that d is c times c plus e. That's what we know. And now we're interested in dd by dc. If you just know your calculus again and you remember, then differentiating c plus e with respect to c, you know that that gives you 1.0.
Wait, what am I saying? This time is plus, this time is not times with different operation. I'm completely cooked. What?
And dd by dc.
Okay. Help me break down this derivative math problem into small steps. Use simple terms. Problem asks us to find dd divided by dc, which means we need to find the derivative of d with respect to c. We're given the equation d equals c plus e. To find d dc, we need to differentiate both sides of the equation with respect to c. On the left side, we'll have d dc. On the right side, we'll differentiate c plus e with respect to c. What? Let's look at the right side, c plus e. Okay, break it down even further. Use LaTeX to visualize each small step. Can it use LaTeX? Can. We start with the given equation, d equals c plus e. We're asked to find dd divided by dc, which is the derivative of d with respect to c. To find this, we apply the differentiation operator both sides. Okay, this step is kinda sketchy. Start with the equation. Find dd, we need to differentiate both sides with respect to c. Oh. We just take this. The thing that's confusing, like unnecessarily, is that we're using d for the, variable as well as for derivative, which is just unnecessary. Okay. How about we use a different letter for the variable? Let's revise the problem using a different letter for a variable. Let's use y instead of d for the dependent variable. Given equation y equals c plus e, we want to find the derivative of y in respect to the derivative of c. Now, step by step, y equals c plus e. Take the derivative of both sides with respect to c. This derivative of y, the derivative of c plus e. The left side becomes our target, yes. Differentiate each term on the right side. E is a constant. Derivative of c with respect to c1. Yes, we learned that. E is a constant, derivative 0. I mean, yeah, it's what Karpathy figured out, but like, I don't know. Still not clicking for me. Let's try this prompt. Looking at the image we have. Okay. Whoa, I didn't mean to just done that. Let's break it down. What does dd mean? This is asking how much does d change when c changes. It's like asking if c increases by 1, how much does d increase? How much does d change when c changes. Let's look up at the equation d equals c plus e. D is made up of two parts, c and e. E is just some constant number that doesn't change. Yes. Now, think about what happens when c changes. C increases by 1, what happens to d? You also increase by 1 because e doesn't change. For every 1 unit c increases d. Why were we doing the differential equation then? This explanation is like 50 times simpler.
If you just know your calculus again and you remember, then differentiating c plus e with respect to c, you know that that gives you 1.0. And we can also go back to the basics and derive this. Because again, we can go to our f of x plus h minus f of x divided by h. That's the definition of a derivative as h goes to 0. And so here, focusing on c and its effect on d, we can basically do the f of x plus h will be c is incremented by h plus e. That's the first evaluation of our function, minus c plus e. And then divide h. And so what is this? Just expanding this.
Why is this so simple, but at the same time feels so complex? Because like when he writes it out like this, I'm like, what? Why am I? This is like so obvious. But when it like does the differential equations, maybe like I'm not familiar with the notation. This is unnecessarily complicated. When he breaks this down, you can just see how it cancels out.
This out, this will be c plus h plus e minus divide h. And then you see here how c minus c cancels, e minus e cancels. We're left with h over h, which is 1.0. And so by symmetry also, d by d e will be 1.0 as well. So basically the derivative of a sum expression is very simple. And this is the local derivative. So I call this the local derivative because we have the final output value all the way at the end of this graph. And we're now like a small node here. And this is a little plus node. And the little plus node doesn't know anything about the rest.
So the plus node is just 1. This is if the other is a constant.
Of the graph that it's embedded in. All it knows is that it did a plus. It took a c and an e, added them, and created a d. And this plus node also knows the local influence of c on d, or rather the derivative of d with respect to c, and it also knows the derivative of d with respect to e. But that's not what we want. That's just a local derivative. What we actually want is dl by dc. And L is here just one step away, but in a general case, this little plus node could be embedded in like a massive graph. So again, we know how L impacts D, and now we know how C and E impact D. How do we put that information together to arrive dL by dC? And the answer, of course, is the chain rule in calculus. And so I pulled up a chain rule here from Wikipedia.
Yeah, of course. Of course, that's the answer.
I'm going to go through this very briefly. So chain rule, Wikipedia sometimes can be very confusing, and calculus can be very confusing. Like, this is the way I learned chain rule, and it was very confusing. Like, what is happening? It's just complicated. So I like this expression much better. If a variable z depends on a variable y, which itself depends on a variable x, then z depends on x as well, obviously, through the intermediate variable y. And in this case, the chain rule is expressed as, if you want dz by dx, then you take the dz by dy and you multiply it by dy by dx. So the chain rule fundamentally is telling you how we chain these derivatives together correctly. So to differentiate through a function composition, we have to apply a multiplication of those derivatives. So that's really what chain rule is telling us. And there's a nice little intuitive explanation. We chain these, you take this as well, obviously, through the intermediate variable y. And
it's kind of funny because the more like advanced you go in neural networks and machine learning, the more it's just like math, right? Like we're not doing much of like learning programming. It's more of like learning math, and then obviously like programming is related.
The chain rule is expressed as, if you want dz by dx, then you take the dz by dy and you multiply it by dy by dx. So the chain rule fundamentally is telling you how we, then z depends on x as well, obviously, through the intermediate variable y. And in this case, the chain rule is expressed as, if you want dz by dx, then you take the dz by dy and you multiply it by dy by dx. So the chain rule fundamentally is telling you how we chain these derivatives together correctly. So to differentiate through a function composition, we have to apply a multiplication of those derivatives. So that's really what chain rule is telling us. And there's a nice little intuitive explanation here, which I also think is kind of cute. The chain rule states that knowing the instantaneous rate of change of z with respect to y and y relative to x allows one to calculate the instantaneous rate of change of z relative to x as a product of those two rates of change, simply the product of those two. So here's a good one. If a car travels twice as fast as a bicycle and the bicycle is 4 times as fast as a walking man, then the car travels 2 times 4, 8 times as fast as the man. And so this makes it very clear that the correct thing to do sort of is to multiply. So
I mean, dude, like the fact that even the word product is not obvious to me when it's the result of multiplication. Yeah.
Car is twice as fast as bicycle, and bicycle is 4 times as fast as man. So the car will be 8 times as fast as the man. And so we can take these intermediate rates of change, if you will, and multiply them together. And that justifies the chain rule intuitively. So have a look at chain rule, but here really what it means for us is there's a very simple recipe for deriving what we want, which is dl by dc. And what we have so far is we know want, and we know what is the impact of d on L. So we know dl by dd, the derivative of L with respect to dd, for deriving what we want, which is dl by dc.
I really need to make sure I don't let myself like get lost, because you know we still have a bunch of to go. There's still plenty of Karpathy to go. So if I get lost now, I'm screwed. So I need to like be on top of things.
And so have a look at chain rule, but here really what it means for us is there's a very simple recipe for deriving what we want, which is dl by dc. And what we have so far is we know want, and we know what is the impact of d on L. So we know dl by dd, the derivative of L with respect to dd. We know that that's -2.
Yes.
And now, because of this local reasoning that we've done here, we know dd by dc. So how does c impact d?
1.
And in particular, this is a plus node, so the local derivative is simply 1.0. It's very simple. And so the chain rule tells us that dl by dc, going through this intermediate variable, will just be simply dl by dd times dd by dc. That's chain rule. So this is identical to what's happening here, except z is RL, y is RD, and x is RC. So we literally just have to multiply these. And because these local derivatives, like dd by dc, are just 1, we basically just copy over dl by dd, because this is just times 1. So what is it? So because dl by dd is -2, what is dl by dc? Well, it's the local gradient 1.0 times dl by dt, which is -2. So literally what a plus node does, you can look at it that way, is it literally just routes the gradient because the plus node's local derivatives are just 1. And so in the chain rule, 1 times dl by dt is just dl by dt. And so that derivative just gets routed to both c and to e in this case. So basically, we have that e dot grad, or let's start with c, since that's the one.
So we set this manually, and then we re-render the graph. Okay. See that grad equals minus 2.0. Do the same for e. So we have figured out three-quarters of the way. Now we need to do A and B with the same rule, which we know. Multiplication again. So the grad should be 2 and minus 3. So B effect on L should be minus 4, and A effect on L should be plus 6. Let's see.
What we've looked at is -2 times 1, -2. And in the same way, by symmetry, e dot grad will be -2. That's the claim. So we can set those, we can redraw, and you see how we just assign -2, -2? So this backpropagating signal, which is carrying the information of like, what is the derivative of L with respect to all the intermediate nodes?
Oh, okay, so I'm starting to understand backpropagation. First we set the numbers and then we backpropagate the gradient. Wait, let me confirm this. I think I'm starting to understand the concept of backpropagation in neural networks. First, in the forward pass, we find the values of each layer, finishing with the output layer, and then in the backward pass, we backpropagate through the entire network, finding the gradient for each node, starting with output and going towards input layer. Is this explanation correct? If not, point out the holes in my understanding. Your understanding of backpropagation is on the right track, but let's clarify and expand on it a bit to ensure a thorough understanding. Forward pass. You're correct about the forward pass. During this phase, input data is fed to the network. The data flows through each layer, with each neuron performing its calculations. The final output is produced at the output layer. Backwards pass, backpropagation. Your explanation of the backward pass is generally correct, but let's add some important details. We start by calculating the error at the output layer by comparing the network's prediction with the target values. Guess we're not there yet. We haven't done any error calculation. We then work backwards through the network layer by layer to calculate the gradients. However, it's important to note we're not just finding gradient for each node, but both for weights and biases. We use the chain rule of calculus to propagate the error backwards. Yeah, right now we don't have this because super simple explanation. Okay.
We can imagine it almost like flowing backwards through the graph, and a plus node will simply distribute the derivative to all the leaf nodes, to all the children nodes of it. So this is the claim, and now let's verify it. So let me remove the plus h here from before. And now instead what we want to do is we want to increment c. So c.data will be incremented by h. And when I run this, we expect to see -2.
Yes.
Negative.
I still need this explained. Okay. Okay, so why in this code does the variable h let us see the derivative? Why? I mean, when I break it down in the equations and cancel everything out, I can get to the right result. But I don't have the intuitive understanding of the role of h in this code and how it lets us see the derivative. Great question. The variable h in this code is being used to implement a numerical method for approximating derivatives called the finite difference method. Let's break this down into intuitive understanding. Small change. H represents a very small change, in this case 0.001, that we're applying to one of the input variables, c in this case. Approximating the derivative. By calculating the function's output before and after the small change, we can approximate the derivative. How it works: we calculate L1 with the original values, we calculate L2 after adding h to c. The formula L2 minus L1 approximates the derivative of L1 with respect to c. Why this works? The definition of derivative is the rate of change of a function as the input changes. Mathematically, it's expressed as so h close to 0. L1 is your position at a certain time. L2 is your position a split second later. L2 minus L1 is the distance you've traveled. H2 is that timer of time. L2 minus L1 divided by h gives you your speed, which is the derivative of position with respect to time. In our code, instead of time, we're changing one of the input variables c by a tiny amount and seeing how much the output L changes. Why it's approximate? Keep exploring. How does change the value? Why is h set to typical? Let's go with this one. In numerical differentiation, h is typically set to a small value for several important reasons. The fundamental idea of numerical differentiation is to approximate the derivative using the definition. Okay, let's continue.
-2. And then, of course, for E, so E.data plus equals H.
I mean, this explanation was kind of good, to be honest. This intuitive understanding. L1 is your position at a certain time, L2 is your position split second later. But shouldn't this also work with larger numbers? Like, you know, why doesn't it work with 5? Oh, it does work. Okay, what about 500? Why are we going with the... Oh. I don't know. Okay, I guess... Let me change this prompt. I guess what I don't understand is why we are going with a very low number when this still works if I make... Okay, even when I make H equals 5000, the result is still correct. Minus 2.0, whatever. Oh, because it's a linear function, then it works. Okay, so yeah. If it was a curve, then you would just miss the curve completely.
And we expect to see -2. Simple. So those are the derivatives of these internal nodes. And now we're going to recurse our way backwards again. And we're again going to apply the chain rule. So here we go, our second application of chain rule, and we will apply it all the way through the graph. We just happen to only have one more node remaining.
So again, as I said, like A effect. Oh, yes, it flipped. Okay, whatever. A effect on L should be +6, and B effect on L should be -4.
We have that dl by dE, as we have just calculated, is -2. So we know that. So we know the derivative of L with respect to E. And now we want dl by dA, right? And the chain rule is telling us that that's just dl by dE, -2, times the local gradient. So what is the local gradient? Basically dE by dA. We have to look at that. So I'm a little times node inside a massive graph, and I only know that I did A times B, and I produced an E. So now what is dE by dA and dE by dB? That's the only thing that I sort of know about. That's my local gradient. So because we have that E is A times B, we're asking what is dE by dA? And of course, we just did that here. We had a times, so I'm not going to rederive it. But if you want to differentiate this with respect to A, you'll just get B, right? The value of B, which in this case is -3.0. So basically we have that dl by dA. Well, let me just do it right here. We have that A.grad, and we are applying chain rule here, is dl by dE, which we see here is -2, times, what is dE by dA? it's the value of b, which is -3. That's it. And then we have b.grad is again dl by de, which is -2.
Let's see.
Just the same way, times what is dE by dB is the value of A, which is 2.0. That's the value of A. So these are our claimed derivatives. Let's redraw. And we see here that A.grad turns out to be 6 because that is -2 times -3. And B.grad is -4 times, is -2 times 2, which is -4. So those are our claims. Let's delete this and let's verify them. We have A here, A.data plus equals H.
Okay, let's verify it then. Of course, we have to delete this line of code. Run it. And it's 0. Why? Why is it 0? Oh, it should be A.data. Come on. Yeah, 6. Okay, verified.
So the claim is that A.grad is 6. Let's verify. 6. And we have B.data plus equals H. So nudging B by H and looking at what happens, we claim it's -4. And indeed, it's -4 plus minus, again, float oddness. That's it. That was the manual backpropagation all the way from here to all the leaf nodes. And we've done it piece by piece. And really all we've done is, as you saw, we iterated through all the nodes one by one and locally applied the chain rule. We always know what is the derivative of L with respect to this little output. And then we look at how this output was produced. This output was produced through some operation, and we have the pointers to the children nodes of this operation. And so in this little operation, we know what the local derivatives are, and we just multiply them onto the derivative always. So we just go through and recursively multiply on the local derivatives. And that's what backpropagation is just a recursive application of chain rule operation. And we have the pointers to the children nodes of this operation, piece by piece.
I feel like this explanation is really, yeah, this is like most replayed.
And really all we've done is, as you saw, we iterated through all the nodes one by one and locally applied the chain rule. We always know what is the derivative of L with respect to this little output. And then we look at how this output was produced. This output was produced through some operation, and we have the pointers to the children nodes of this operation. And so in this little operation, we know what the local derivatives are, and we just multiply them onto the derivative always. So to all the leaf nodes. And we've done it piece by piece. And really all we've done is, as you saw, we iterated through all the nodes one by one and locally applied the chain rule. We always know what is the derivative of L with respect to this little output. And then we look at how this output was produced. This output was produced through some operation, and we have the pointers to the children nodes of this operation. And so in this little operation, we know what the local derivatives are, and we just multiply them onto the derivative always. So we just go through and recursively multiply on the local derivatives. And that's what backpropagation is just a recursive application of chain rule backwards through the computation graph. Let's see this power in action just very briefly. What we're going to do is we're going to nudge our inputs to try to make L go up. So in particular, what we're doing is we want A.data, we're going to change it. And if we want L to go up, that means we just have to go in the direction of the gradient. So A should increase in the direction of gradient by like some small step amount. This is the step size. And we
This part I still don't have the intuition for.
To try to make L go up. So in particular, let's see this power in action just very briefly. What we're going to do is we're going to nudge our inputs to try to make L go up. So in particular, what we're doing is we want a.data, we're going to change it. And if we want L to go up, that means we just have to go in the direction of the gradient. So A should increase in the direction of gradient by like some small step amount. This is the step size. And we don't just want this for B, but also for B, also for C, also for F. Those are leaf nodes, which we usually have control over. And if we nudge in direction of the gradient, we expect a positive influence on L. So we expect L to go up positively. So it should become less negative. It should go up to say negative 6 or something like that. It's hard to tell exactly. And we'd have to rerun the forward pass. So let me just do that here. This would be the forward pass. F would be unchanged. This is effectively the forward pass. And now if we print L.data, we expect, because we nudged all the values, all the inputs in the direction of gradient, we expected a less negative L. We expect it to go up. So maybe it's negative 6 or so. Let's see what happens. Okay, negative 7. And this is basically one step of an optimization that will end up running. And really, this gradient just give us some power because we know how to influence the final outcome.
Oh, now that you know the gradients for each of the nodes, you can apply the number to nudge it in the right direction to get the desired effect on the loss function. Damn, that's nice.
The local derivatives. And that's what backpropagation is. It's just a recursive application of chain rule backwards through the computation graph. Let's see this power in action just very briefly. What we're going to do is we're going to nudge our inputs to try to make L go up.
Let's see where I'm at in this.
So in particular, what we're doing is we want a.data, we're going to change it. And if we want L to go up, that means we just have to go in the direction of the gradient. So A should increase in the direction of gradient by like some...
Okay. A.data plus equals 0.01 times A.grad. We copy this for every, for B as well. And for C as well. Well, actually, yeah, for C and then F. Only the ones that we are adding, not the ones that are going to be the result, because, or the product, you know, because they're already impacted by this. So, now F. I think he did more.
For B, also for F. Those are leaf nodes, which we usually have control
Leaf
over.
nodes.
And if we nudge in direction of the gradient, we expect a positive influence on L. So we expect L to go up positively. So it should become less negative. It should go up to say negative 6 or something like that. It's hard to tell exactly. And we'd have to rerun the forward pass. So let me just do that here. Data.
E equals A times B. D equals E plus C. L equals D times F. Can print L.data. Oh, we need to... Oh, this is gonna ruin our chart, I think. We disconnected from the runtime. Yeah, it indeed did ruin our chart.
We expect, because we nudged all the values, all the inputs in the direction of gradient, we expected a less negative L. We expect it to go up. So maybe it's -6 or so. Let's see what happens. Okay, negative.
Okay, that did not happen for us because... Why? Oh, we don't have the gradient set. So we're not adding anything. Oh my god. Okay, let's just manually set the gradients based on what we had. So, you know, here it's...
So
it was like reverse, right? So let's see, f dot grad equals 4.0, d dot grad equals minus 2.0, and then we can literally do the same for C and E. I think. Yes. And then down here we just like multiplied by minus 2, so A is minus 3, so that's 6. A dot grad was 6.0, and B dot grad equals minus 4.0. Let's run this, and then we can delete it. Oops. We can run this. Yeah, nice. Beautiful.
maybe it's -6 or so. Let's see what happens. Okay, -7. And this is basically one step of an optimization that we'll end up running. And really, this gradient just give us some power because we know how to influence the final outcome. And this will be extremely useful for training neural nets, as we'll soon see. So now I would like to do one more. This will be the forward pass.
What happened?
Forward pass. So let me just get to go up. So end up running. And really, this gradient just give us some power because we know how to influence the final outcome. And this will be extremely useful for training neural nets, as we'll soon see. So now I would like to do one more example of manual backpropagation using a bit more complex and useful example.
It's such a, like, you know, checkpoint in the video when you see like, okay, now we've been doing some advanced stuff, and then, you know, Andrej Karpathy just says, now let's do something a bit more complex. It's like, oh my god. It's like, happens multiple times throughout the video. It's like, whew, reality check every time, you know? Like, there's levels to this S. And we're not even, you know, we're like, this is beginner's level. Yeah, I need to really step my programming, math, and machine learning up. Whew.
We are going to backpropagate through a neuron. So we want to eventually build out neural networks. And in the simplest case, these are multilayer perceptrons, as they're called. So this is a 2-layer neural net. And it's got these hidden layers made up of neurons, and these neurons are fully connected to each other. Now, biologically, neurons are very complicated devices, but we have very simple mathematical models of them. And so this is a very simple mathematical model of a neuron. You have some inputs, X's, and then you have these synapses that have weights on them. So the W's are weights. And then the synapse interacts with the input to this neuron multiplicatively. So what flows to the cell body of this neuron is W times X. But there's multiple inputs, so there's many W times X's flowing to the cell body. The cell body then has also like some bias. So this is kind of like the innate sort of trigger happiness of this neuron.
So that's where the term weights and biases comes from.
So this bias can make it a bit more trigger happy or a bit less trigger happy.
Also, that's interesting because every cell has like a inherent characteristic. You can think of it almost like a personality, which like alters the weight and synapse coming forward.
Of this neuron is W times X. And then the synapse interacts with the input to this neuron multiplicatively. So what flows to the cell body of this neuron is W times X. But there's multiple inputs, so there's many W times X's flowing into the cell body. The cell body then has also like some bias. So this is kind of like the innate sort of trigger happiness of this neuron. So this bias can make it a bit more trigger happy or a bit less trigger happy, regardless of the input. But basically, we're taking all the W times X of all the inputs, adding the bias, and then we take it through an activation function. And this activation function is usually some kind of a squashing function, like a sigmoid or tanh or something like that. So as an example, we're going to use the tanh in this example. NumPy has a np.tanh, so we can call it on a range, and we can plot it.
Wait a second. Link this beta data, okay. Beta data plus equals h, right? Yeah. And then matplotlib plt.plot np.arrange. We've already learned the syntax. -5, 5, and the increment is 0.2 this time. Oops. Not sure why that resets. Okay. np.tanh, np.arrange. Same. Plot that grid. I don't know why Karpathy uses the semicolon instead of writing it on a separate line, like it's conventional, but I guess Andrej Karpathy is anything but conventional. So yeah, we have a nice little tangent.
This is the tanh function, and you see that the inputs, as they come in, get squashed on the y coordinate here. So right at 0, we're going to get exactly 0. And then as you go more positive in the input, then you'll see that the function will only go up to 1 and then plateau out. And so if you pass in very positive inputs, we're going to cap it smoothly at 1. And on the negative side, we're going to cap it smoothly to -1. So that's tanh. And that's the squashing function or an activation function. And what comes out of this neuron is just the activation function applied to the dot product of the weights and the inputs. So let's write one out. I'm going to copy paste because I don't want to type too much, but I guess.
Fair enough, fair enough. But let's see.
So here we have the inputs, x1, x2. So this is a two-dimensional neuron. So two inputs are going to come in. These are thought of as the weights of this neuron. Weights W1, W2. And these weights, again, are the synaptic.
Okay, let's write this out. Inputs, x1, x2. X value 2. x1 equals value object 0.0 label equals x1. x2 equals value 0.0 label x2. Perfect. Now weights. W1, W2. also value objects, -3 and 1. W1, W2 equals value 1, 0. Okay.
Synaptic strengths for each input. And this is the bias of the neuron, B. And now what we want to do is
Beautiful. Bias of your neuron. B equals value 6.7. Okay.
according to this model, we need to multiply x1 times w1 and x2 times w2, and then we need to add bias on top of it. And it gets a little messy here, but all we are trying to do is x1 w1 plus x2 w2 plus b. And these.
Why does it get messy? Oh, I guess because we want to set the labels for everything as well.
These are multiplied here. Except I'm doing it in small steps so that we actually have pointers to all these intermediate nodes. So we have x1 w1 variable, x2 w2 variable, and I'm also labeling them. So
let's write this out. x1 times x1 w1 plus x2 times w2 plus b. And then just assign it, declare the variable, and then in the same line we add the label. x1 w1 equals x1 times w1 x1 w1 dot label equals x1 w1. I have to do it at the end. Obviously this is Python w1, and then we do the same literally. Oops, this should be incorrect. I'm gonna copy paste this, place all the ones with 2s. Honestly, what am I doing? Control H, find 1, replace with 2. Replace. Close. Okay. That's that. And now we're doing this long, you know, this, whatever this is. And N, I guess that's the neuron, equals this crazy variable plus b plus the bias, and then label, yeah, and that label equals n.
N is now the cell body raw activation without the activation function for now. And this should be enough to basically plot it. So draw dot of n.
Whoa! Forgot we had this function. Draw dot of n. Wait a minute. Something ain't quite right. Did I forget to set a value object somewhere? What is wrong? Why am I not getting the entire tree? Only n. Something with the draw dot function that was not updated. Let me compare these two codes. Do writing, and I need to make sure that we have everything. Code 1. Code 2. List out all the key differences between these two pieces of code. Oh, the label. Different labels here. That shouldn't change anything. Final calculation equals, oh my god. Of course I trolled it. I just equaled it to B. That's crazy. Yeah, this is more like it. We nice to see the bias being applied here. This is nice. Man, visualizing stuff is kind of addictive. I don't know. Learn Matplotlib more, for sure. But this doesn't count the gradient descent. I guess that's where the term gradient descent comes from. Gradient descent in neural networks. Use simple terms. Why is it searching so hard? Yeah, the main goal of gradient descent, find the best weights. Gradient descent helps us figure out how to change. Or loss. But break down the term itself, gradient. Help me understand term. A gradient is a vector that points in the direction of the steepest increase of a function. It represents the slope or rate of change of a function in multiple dimensions. Gradient tells us which direction to move in order to increase the function values most rapidly. Descent means going downward or moving from a higher to a lower level. In the context of optimization, should have said in the context of AI. Gradient refers to the slope or steepness of a function at a given point. In AI, this typically relates to the slope of the error cost function that measures how well the model is performing. Descent means going downward or decreasing. In AI, this refers to the process of iteratively moving downward along the slope of the error function to find its minimum. Put together, gradient descent describes an optimization algorithm that calculates the gradient slope of the error function, updates those parameters by taking a step in the direction of the steepest descent, opposite the gradient. The key ideas are using the gradient to determine which direction to move, moving downhill to minimize error. Okay.
Gives us x1 times w1, x2 times w2 being added. Then the bias gets added on top of this. And this n is this sum. So we're now going to take it through an activation function. And let's say we use the tanh so that we produce the output. So what we'd like to do here is we'd like to do the output, and I'll call it O, is n dot tanh.
Okay. O is n dot tanh.
Okay, but we haven't yet written the tanh. Now, the reason that we need to implement another tanh function here is that tanh is a hyperbolic function, and we've only so far implemented a plus and a times, and you can't make a tanh out of just pluses and times. You also need exponentiation. So tanh is this kind of a formula here. You can use either one of these, and you see that
Hyperbolic tangent.
There's exponentiation involved, which we have not implemented yet for our low value node here. There's exponentiation involved.
Sinus, cosine, sine, cosine, h, hyperbolic sine, hyperbolic cosine.
Which we have not implemented yet for our low value node here. So we're not going to be able to produce tanh yet, and we have to go back up and implement something like it. Now, one option here.
Wait, what?
You also need exponentiation. So tanh is this kind of a formula here. You can use either one of these, and you see that there's exponentiation involved, which we have not implemented yet for our low value node here. So we're not.
That's right. We don't have, and we don't have division, and we don't have exponentiation implemented in the dunder methods, right? Dunder D. Yeah, we have only add and multiply. Addition, multiplication.
Produce tanh yet, and we have to go back up and implement something like it. Now, one option here is we could actually implement exponentiation, right? And we could return the exp of a value instead of a tanh of a value. Because if we had exp, then we have everything else that we need. So
yeah, we can like construct this nh.
Because we know how to add, and we know how to add, and we know how to multiply. So we'd be able to create tanh if we knew how to exp. But for the purposes of this example, I specifically wanted to show you that we don't necessarily need to have the most atomic pieces in this value object. We can actually like create functions at arbitrary points of abstraction. They can be complicated functions, but they can be also very, very simple functions like a plus. And it's totally up to us. The only thing that matters is that we know how to differentiate through any one function. So we take some inputs and we make an output. The only thing that matters, it can be arbitrarily complex function, as long as you know how to create the local derivative. If you know the local derivative of how the inputs impact the output, then that's all you need. So we're going to cluster up all of this expression, and we're not going to break it down to its atomic pieces. We're just going to directly implement tanh. So let's do that. Def tanh, and then out will be a value of, and we need this expression here. So
I got a little bit lost in thought there.
For up, as long as you know how it matters, is that we know how to differentiate through any one function. So we take some inputs and we make an output. The only thing that matters, it can be arbitrarily complex function, as long as you know how to create the local derivative. If you know the local derivative of how the inputs impact the output, then that's all you need. So we're going to cluster up all of this expression, and we're not going to break it down to its atomic pieces. we're just going to directly implement tanh. So let's do that. Def tanh, and then out will be a value of
on the data.
And we need this expression here. So,
we just, okay, so we don't need to do it on the value object. We just do it inside of it. Okay. Here already. Def tanh. Keep forgetting this. Output equals value.
Let me actually copy paste. Let's grab n, which is solve.data, and then this, I believe, is the tanh.
You just cooked that up out of nowhere.
Math.exp of
n equals self.data above the output. Self.data. And then t, and that's the expression. Math, okay, time for a split screen. Okay, d equals math dot exp, because that's built in Python function, -1 divided by math. We're just like literally rewriting the Wikipedia definition of hyperbolic tangents. Okay.
n minus 1 over 2n plus 1. Maybe I can call this x, just so that it matches exactly.
Let's call this x.
Okay, and now this will be t, and children of this node, there's just one child, and I'm wrapping it in a tuple, so this is a tuple of one object, just self.
Just one child. Tangent. The activation function, so we need the child. Wait.
T, and children of this node, there's just one child, and I'm wrapping it in a tuple, so this is a tuple of one object, just self. And here, the name of this operation will be tanh, and we're going to return that. Okay. So now values should be implementing tanh, and now we can scroll all the way down here, and we can actually do n.tanh, and that's going to return the tanh output of n. And now we should be able to draw it out of O, not of n. So let's see how that worked. There we go. N went through tanh to produce.
Whoa, do I have that? Wait a minute. N. Oh, I do have that at the very end. Yeah, enough of the split screen. We have it. X1, W1, W2 through multiplication. Then addition. The bias was added, which then went end, and then tanh, and the final result without a label.
So now tanh is a...
Yeah, we haven't given it a label O.
Our little micrograd supported node here as an operation.
Wait, shouldn't we do that? Like, you know, O dot label equals O. Why not?
And as long as we know the derivative of 10h, then we'll be able to backpropagate through it. Now let's see this 10h in action. Currently it's not squashing too much because the input to it is pretty low. So if the bias was increased to say 8, then we'll see that what's flowing into the 10h now is 2.
Oh, okay, yeah. So remember, it's like squashing down between -1 and +1, but since already n is 0.7, it's like the effect is not that drastic. But if we step up the bias to like 50, then we go from 44 to 1. A huge decrease, right? You went for 8. .96 from 2.
And 10h is squashing it to 0.96. So we're already hitting the tail of this 10h, and it will sort of smoothly go up to 1 and then plateau out over there. Okay, so now I'm going to do something slightly strange. I'm going to change this bias from 8 to this number, 6.88, etc.
All right,
And I'm going to do this for specific reasons because we're about to start backpropagation, and I want to make sure that our numbers come out nice.
Okay. Sure. We have the number.
They're not like very crazy numbers. They're nice numbers that we can sort of understand in our head. Let me also add O's label. O is short for output here. So that's the R. Okay, so 0.88 flows into 10h, comes out 0.7, so on. So now we're going to do backpropagation, and we're going to fill in all the gradients. So what is the derivative O with respect to all the inputs here? And of course, in a typical neural network setting, what we really care about the most is the derivative of these neurons on the weights specifically, the W2 and W1, because those are the weights that we're going to be changing part of the optimization. And the other thing that we have to remember is here we have only a single neuron, but in a neural net you typically have many neurons and they're connected. So this is only like one small neuron, a piece of a much bigger puzzle, and eventually there's a loss function that sort of measures the accuracy of the neural net, and we're backpropagating with respect to that accuracy and trying to increase it. So let's start off backpropagation here in the end. What is the derivative of O with respect to O? The base case, sort of, we know always, is that the gradient is just 1.0.
Yes.
So,
at least I'm learning something. Oh, I just realized that the shortcut Control plus M plus B stands for below, probably, and A stands for above. At least that's what I think. Anyways, O dot grad equals 1.
So let me fill it in, and then let me split out the drawing function here. And then here, cell clear this output here. Okay.
Sure. Control X. Tools. Edit. We can just click on clear selected output. Okay.
So now when we draw O, we'll see that that grad is 1. So now
We need to run this and read about this. Beautiful.
now we're going to backpropagate through the 10h. So to backpropagate through 10h, we need to know the local derivative of 10h. So if we have that O is 10h of n, then what is dO by dn? Now what you could do is you could come here and you could take this expression.
dO by dn.
and you could do your calculus derivative taking, and that would work. But we can also just scroll down Wikipedia here.
Sure.
Into a section that hopefully tells us that derivative d by dx of 10h of x is any of these. I like this one, 1 minus 10h squared of x. So this is 1 minus 10h of x squared. So basically what this is saying is that do by dn is 1 minus 10h of n squared. And we already have 10h of n, it's just o. So it's 1 minus o squared. So o is the output here. So the output is this number.
Wait, that was kind of beautiful. Wait.
Do by dn.
Derivative o. Derivative of.
Is 1 minus 10h of n squared.
Okay, that's the Wikipedia expression, and then we simplify it because we already have o equals 10h, so we can just replace it with o.
And we already have 10h of n,
simple.
It's just o. So it's 1 minus o squared. So o is the output here. So the output is this number. O dot data is this number. And then what this is saying is that do by dn is 1 minus this squared. So 1 minus o dot data squared is 0.5 conveniently. So the local derivative of this
I guess
10h operation.
that's why we use this precise number, is to get the nice derivative.
Here is 1 minus o dot data squared is 0.5 conveniently. So the local derivative of this 10h operation here is 0.5. And so that would be do by dn. So we can fill in that n dot grad is 0.5. We'll just fill it in. We'll just fill it in.
So we don't have this weird long number. We fill it in manually.
Here is 0.5. And is 0.5 conveniently. So the local derivative of this 10h operation here is 0.5. And so that would be do by dn. So we can fill in that n dot grad is 0.5. We'll just fill it in.
Sure. N dot grad equals 0.5. I feel guilty not doing the calculation myself, but yeah. 1 minus o dot data to the power of 2. Simplified. Redraw. We're doing backpropagation. Amazing.
So this is exactly 0.5, 1/2. So now we're going to continue the backpropagation. This is 0.5, and this is a plus node. So how is backprop going to, what is backprop going to do here? And if you remember our previous example, a plus
just passes it down.
Plus is just a distributor of gradient. So this gradient will simply flow to both of these equally. And that's because the local derivative of this operation is 1 for every one of its nodes. So 1 times 0.5 is 0.5. So therefore, we know that
we can just manually set it. Kind of feels wrong setting the values manually, but whatever. Got the approval of Andrej Karpathy. You gonna need to get this weird variable name. Redraw. Gradient is descending.
This node here, which we called this, its grad is just 0.5. And we know that b dot grad is also 0.5. So let's set those and let's draw. So those are 0.5. Continuing, we have another plus. 0.5 again, we'll just
Another plus. Oh my god, how convenient. So we need these two. Just copy this. Okay.
just distribute it. So 0.5 will flow to both of these. So we can set theirs. X2 W2 as well. That grad is 0.5 as well. And let's redraw. Pluses are my favorite operations to backpropagate through because it's very simple. So now what's flowing into these expressions is 0.5. And so really, again, keep in mind what the derivative is telling us at every point in time along here. This is saying that if we want the output of this neuron to increase, then the influence on these expressions is positive on the output. Both of them are positive contribution to the output. So now backpropagating to x2 and w2 first. This is a times node. So we know that the local derivative is, the other term. So if we want to calculate x2.grad, then can you think through what it's
You can just do w2.data, no?
going to be? So x2.grad
What is this awkward pause?
will be w2.data
Oh my god. Oh, times?
times.
Oh, Jesus. Why am I so dumb? Oh my god. Of course it's times the previous gradient. Never mind. I had this little moment of... Yeah. Let's ignore that. x1 dot grad equals w1 dot data times 0.5. And then we do that for all the other expressions as well. Well, actually, let's do a new field, because this one is already proven. Let's do above. Closer. Equals x1 dot data times 0.5. We repeat this for x2 w2. x2 place 2 everywhere. Run it, redraw, and then we should get the final gradients: minus 1.5, 1, 0, 0.5.
This x2w2.grad, right? And w2.grad will be x2.data times x2w2.grad. Right? So that's the...
I mean, yeah, I just typed it manually, but probably better to... probably better to set it, like, actually. From what it's coming in, right? So this is coming in, meaning, yeah, this is like the cheeky way to do it, but the better way to do it, like good practice, is just looking what's descending. So from x1 w1 we have this, variable. We can just do this dot grad, and it should be for both. Obviously it's going to equal the same thing, but good practice to do it like so.
Local piece of chain rule. Let's set them and let's redraw. So here we see that the gradient...
Wait, what? Set them a redraw? Did I do something incorrectly? 0.50. My data is wrong. Why is my data wrong? Did he change it? Why is the data different? 0, 1, 2, minus 3? Where? Zero. My data is correct. Am I crazy here? What's happening? Multiplication, redraw. Did I do it wrong? xw data. What is going on? Surely I must have messed up somewhere. Grad is 1. Yeah. Is my grad is correct here? Then here it's why? Okay, surely I'm messing up somehow. X1 W1 data times X1 W1 X2 W2 dot grad. What?
On our weight 2 is 0 because x2's data was 0, right? But x2 will have the gradient 0.5 because data here was 1. And so what's interesting here, right, is because the input x2...
Oh my god, he hasn't written the lines yet. What am I doing?
It was 0. Then because of the way the times works, of course, this gradient will be 0. And think about intuitively why that is. Derivative always tells us the influence of this on the final output. If I wiggle W2, how is the output changing? It's not changing because we're multiplying by 0. So because it's not changing, there is no derivative, and 0 is the correct answer because we're squashing it at 0. And let's do it here. 0.5 should come here and flow through this times. And so we'll have that x1.grad is... Can you think through a little bit what
actually, I'm going to do something I haven't done yet. I'm going to skip ahead.
W1.
Just 20 seconds, no big deal, but skipping ahead is kind of a flex.
Grad. Let's see what those came out to be. So this is 0.5, so this would be negative 1.5, and this would be 1. And we've backpropagated through this expression. These are the actual final derivatives. So if we want this neuron's output to increase, we know that what's necessary is that W2, we have no gradient. W2 doesn't actually matter to this neuron right now.
So
but
this is the useless weight. So if we're tuning the weights and we want the result to increase, then we need to, because this is a positive gradient, we need to increase it in a positive direction.
This weight should go up. So if this weight goes up, then this neuron's output would have gone up, and proportionally because the gradient is 1. Okay, so doing the backpropagation
my god, that's why we set it to this strange number, so that it comes out to beautiful 1. And the other weight is 0, so only this weight matters, and it's like exact same influence on the output O as the weight. Yeah, this number for our current situation makes it happen.
Is obviously ridiculous, so we are now going to put an n up. Then this neuron's output would have gone up, and proportionally because the gradient is 1. Okay, so doing the backpropagation manually is obviously ridiculous.
Okay, good.
So we are now going to put an end to this suffering, and we're going to see how we can implement the backward pass a bit more automatically. We're not going to be doing all of it manually out here. It's now pretty obvious to us by example how these pluses and times are backpropagating gradients. So let's go up to the value object, and we're going to start codifying what we've seen in the examples below. So we're going to do this by storing a special self.backward.
Okay, so starting with underscore, meaning it's not going to be visible anywhere. I mean, you can tell, right? Because label we've set outside of the class, but everything else we're just not referencing. I mean, yeah, data and grad as well. So the stuff that it's literally such a good habit and such a simple lesson. Just like whatever you start with an underscore, you should not. The intent is that it's meant to be private. It shouldn't be used outside of this function, outside of building it of the class.
And
all of that backward, okay? self dot backward.
Underscore backward. And this will be a function which is going to do that little piece of chain rule. At each little node that took inputs and produced output,
Are we going to do based on the operation then?
Going to store how we are going to chain the outputs gradient into the inputs gradients. So by default, this will be a function that doesn't do anything.
So lambda is a Python like single line function. Let me just refresh my knowledge on this. Explain lambda in Python. Use simple terms. Let's write it down. We haven't written anything down for a long time. Okay, lambda boom a do Python dot lambda Python underscore lambda boom small anonymous function that you can create quickly and easily. Okay, let me just copy this other thing. Like a shortcut for writing simple functions without giving them a name. Another good sentence here. I'm getting lost here. Man, the perplexity is so useful here. I'm gonna leave a link for it in the description. Perplexity Pro. If you're not paying for Perplexity, what are you doing? Like, look how useful it is for learning new concepts. Literally the best way to browse the web, by far. Okay, here's a breakdown of what that means. Small. Lambda functions are typically used for simple operations that can be written in one line of code. This is probably better. And then anonymous. Unlike regular functions that have names, lambda functions don't have names. They're created and used on the spot. Function. It still does what a function does, takes input and returns an output. The basic structure of a lambda function looks like this. Lambda, arguments, expression. Here's a simple example. A lambda function that adds 5 to a number. Add 5 equals lambda x, the argument, this is the syntax, x plus 5. That's the expression. Using the lambda function, result equals add 5, 10, print result 15.
And you can also see that here in the value in Micrograd. So with this backward function, by default doesn't.
Okay, so colon none equals lambda colon none.
Do anything. This is an empty function. And that would be sort of the case, for example, for a leaf node. For a leaf node, there's nothing to do.
Leaf node. But interesting. That's the terminology for these that come in not from the main tree but are added. Leaf node. Okay. Maybe let's see if Perplexity can explain it. Whatever. I mean, we understand what it is. You don't have to ask Perplexity for everything. So let's run this.
When we're creating these out values are an addition of self and other. And so we'll want to set doesn't do anything. This is an empty function. And that would be sort of the case, for example, for a leaf node. For a leaf node, there's nothing to do. But now when we're creating these out values are an addition of self and other.
So we can set it specific to the addition and multiplication different because, addition it just passes down and multiplication is the other value.
And so
this is going to be nice. This is going to be nice.
We'll want to set outs backward to be the function that propagates the gradient. So let's define what should happen. And we're going to store it in a closure. let's define what should happen when we call out.
Man, his keyboard shortcuts are so nice. Like, whew, I feel like I type way faster than the average person, but I feel super slow compared to Karpathy. Like, look at this.
We'll want to set outs backward to be the function that propagates the gradient. So let's define what should happen.
Okay, out that backward equals backward, and we need to define it then. Define backward.
Happen. And we're going to store it in a closure. Let's define what should happen when we call Autograd. For an addition, our job is to take Autograd and propagate
Autograd output and propagate the cell. Wait. Output of backpropagation and with addition. So do we take self or other? Let's see.
it into self's grad and other.grad. So basically we want to self.grad to something and we want to set others.grad to something.
It's not the child, it's the parent in this case.
Okay. And the way we saw below how chain rule works, we want to take the local derivative times the sort of global derivative, I should call it, which is the derivative of the final output of the expression with respect to outs data.
Okay, so let's implement this, I guess. Other
with respect to out. So the local derivative.
Why am I not using f? Using this
of self in an addition is 1.0. So it's just 1.0.
The derivative of self times
outs grad.
Oh, out. It's the same with other then.
That's the chain rule. And others.grad will be 1.0 times outgrad.
I forgot that out is basically the parent. I was looking for like, do we have to declare a parent? But since this is in a function that creates the parent, basically, we just use that. Beautiful. 1 times 0, 1.0 times out.grad, yeah. Let's copy this. Paste. Wow, so elegant.
And what you're seeing here is that outsgrad will simply be copied onto self's grad and others grad, as we saw happens for an addition operation. So we're going to later call this function to propagate the gradient, having done an addition. Let's now do the multiplication. We're going to also define that backward.
And for multiplication, it's out that. Oh my god! Let me implement it myself, okay? I don't need this shit. Boom. So we do out that gradient times and other that data. Other that data. Am I starting to gain understanding here? Out that backward equals backward. I'm not sure about this line, but these two I'm very sure about.
And we're going to set its backward to be backward. And
wait. He is a... Is this a mistake? Not having the parentheses there? Oh no, there shouldn't be there. Also, that way they're like none, right? Wait. It shouldn't be calling the function in that case. It's just using backward. I don't know. Maybe he'll correct it.
And we want to chain outgrad into self.grad and others.grad. And this will be a little piece of chain rule for multiplication. So we'll have, so what should this be? Can you think through? So what is the local derivative here? The local derivative was others.data, and then, others.data, and then times out.grad. That's chain rule. And here we have self.data times out.grad. That's what we've been doing. And finally here for 10H.
Wait, so do I have it correct? Self.data, other.data times out.grad. Guys, I'm learning. It's crazy. You're watching a neural network learn. This time a biological one.
F backward.
For 10H as well.
And then we want to set out backwards to be just backward. And here we need to...
It's interesting, I'm looking at the final code, but parentheses are not there. It's literally this line. Not here. Here.
Backpropagate, we have out.grad.
Indents matter in Python a lot. Out.grad.
And we want to chain it into self.grad. And self.grad.
This part.
And here we need to backpropagate. We have out.grad, and we want to chain it into self.grad. And self.grad will be the local derivative of this operation that we've done here, which is 10H. And so we saw that the local gradient is 1 minus the 10H of x squared, which here is t. That's the local derivative, because t is the output of this 10H. So 1 minus t squared is the local derivative, and then the gradient has to be multiplied because of the chain rule.
Chain rule, okay. I still need more understanding for the chain rule. Haven't, looked that one up in Perplexity. What am I doing? Here. Self.grad equals, then one minus t to the power of 2. 1 minus t to the power of 2 times Autograd. Yeah, I mean the hyperbolic tangent, that I need to refresh.
So outgrad is chained through the local gradient into self.grad. And that should be basically it. So we're going to redefine our value node. We're going to swing all the way down here, local gradient into self.grad. And that should be basically it. So we're going to redefine our value node. We're going to swing all the way down here.
Okay, maybe let's ask Perplexity about the parentheses. In this code above, does it matter if I have a line like this or a line like this? Or are they the same in effect? Are not the same. This line assigns the function backward to out that backward. It doesn't call the function. It just stores the function itself as an attribute of out. This is the correct approach in this context. This line would immediately call the backward function and assign its return value to our backward. Since backward function doesn't return anything without the return statement, this would actually set out that backward to none. So yeah, it is a mistake. The correct version allows the backward pass to be executed later when needed. It stores the function so it can be called appropriate. Ooh, that's a nice solution.
And we're going to redefine our expression, make sure that all the grads are 0. Okay.
Wait. Slow this down.
And that should be basically it. So we're going to redefine our value node. That should be basically it. So we're going to...
Wait, what? How did he jump down so fast?
And that should be basically it. So we're going to... grad. And that should be basically it. So we're going to...
That's crazy. Did it delete those? Control MD, Control MD. I guess this is just jump to the node below, to the cell below. Let's look that up. What is the collab, Google Colab keyboard shortcut for jump to the cell below? Shift Enter. Oh, so you just like after implementing it, blah blah blah, like delete or whatever, and then Shift Enter. That jumps your cursor to the next one. Yeah, I've been doing Control Enter. But yeah, okay.
Redefine our value node. We're going to swing all the way down here.
Okay. Let's go all the way down here.
And we're going to redefine our expression.
Run it again, I guess.
Make sure that
Rerun this so all gradients are 0.
all the grads are 0. Okay. But now we don't have to do this manually anymore. We are going to basically be calling the dot backward in the right order. So first we want to call oaths dot backward. So O was the outcome of 10H, right? So calling those O's backward will be this function. This is what it will do. Now we have to be careful because there's a times out.grad, and out.grad, remember, is initialized to 0. So here we see grad 0. So as a base case, we need to set oath.grad to 1.0 to initialize this with 1.
Otherwise, it would just be zeros throughout. Interesting how he's splitting it into different cells. I don't know if that's like another like good practice. If there's any like reasoning for that. Let's do that. Rerun.
This is 1. We can call O.backward, and what that should do is it should propagate this grad through 10H. So the local derivative times the global derivative, which is initialized at 1. So this should
So that may be caused by the parentheses, brackets.
Dope. So I thought about redoing it, but I figured I should just leave the error in here because it's pretty funny. Why is NumTyObject not callable? It's because I screwed up. We're trying to save these functions. So this is correct. This here, we don't want to call the function because that returns none. These functions return none. We just want to store the function. So let me redefine the value object. And then we're going to come back and redefine the expression.
Yeah, I mean, Perplexity explained it the same, but I just spotted that by accident, so I'm not going to even pretend like I'm any better, because I didn't know which was the correct, so yeah, whatever.
Expression, draw a dot. Everything is great. O.grad is 1. O.grad is 1. And now this should work, of course.
O dot backward. And we redraw. Boom. Grad 0.5. Beautiful.
Okay. So all that backward should have, this grad should now be 0.5 if we redraw. And if everything went correctly, 0.5. Yay. Okay, so now we need to call ens.grad.
We're just gonna pass it here and it's gonna get 0.5 as well. I mean, it'll be the same result we did when we did the backpropagation manually, but now we're doing it programmatically, which is much better.
Ens.backward, sorry.
Okay. N dot backward. Okay, let's run it. Beautiful, works. That's so nice.
It's backward. So that seems to have worked. So ens.backward routed the gradient to both of these. So this is looking great. Now we could of course call b.grad, b.backward, sorry. What's going to happen? Well,
Nothing.
B doesn't have a backward. B's backward,
It's none.
because B is a leaf node, B's backward is by initialization the empty function. So nothing would happen, but we can call it on it. But when we call this one, it's backward, then we expect
That's a crazy variable name. You should pass again because we have another plus. Beautiful. And now these are going to be interesting.
this 0.5 to get further routed, right? So there we go, 0.5, 0.5. And then finally, we want to call it here on x2, w2, and on x1, w1.
Copy this. Run, redraw, and we got the correct results. You remember? These were the exact same results when we did it manually. Nice.
Let's do both of those. And there we go. So we get 0, 0.5, negative 1.5, and 1, exactly as we did before. But now we've done it through calling that backward sort of manually. So we have one last piece to get rid of, which is us calling underscore backward manually.
Yeah.
So let's think through what we are actually doing. We've laid out a mathematical expression, and now we're trying to go backwards through that expression. So going backwards through the expression just means that we never want to call a dot backward for any node before
it's finished.
We've done sort of everything after it. So we have to do everything after it before we're ever going to call dot backward on any one node. We have to get all of its full dependencies. Everything that it depends on has to propagate to it before we can continue backpropagation. So this...
Well, before we can even start it, no? Not to continue.
Ordering of graphs can be achieved using something called topological sort. So topological sort is basically a laying out of a graph such that all the edges go only from left to right, basically. So here we have a graph, it's a directly acyclic graph, a DAG, and this is two different topological orders of it, I believe, where basically you'll see that it's a laying out of the nodes such that all the edges go only one way, from left to right. And implementing topological sort, you can look in Wikipedia and so on. I'm not going to go through it in detail. But basically, this is what builds a topological graph.
Okay, topological sort. Let's have Perplexity explain that. Explain what topological sort is, how it works. Use simple terms. Isn't there a rewrite with Pro? Is there a button like redo with Pro? Yeah, I needed the... So it only goes in one direction. So in this case, you cannot go to a smaller number. Only to a larger number. Topological sort is an algorithm used to order the nodes in a directed graph based on their dependencies. Imagine you have a list of tasks where some tasks need to be completed before others start. Algorithm looks at a directed graph where each node represents a task and each edge represents a dependency. One task must be. Start by finding nodes that have no incoming edges, no dependencies. These are tasks that can be run right away. It adds these nodes to the sorted list and removes them from the graph along with their outgoing edges. The process is repeated, finding nodes with no incoming edges. Okay, so let's see how it's implemented in code then.
Implementing topological sort, you can look in Wikipedia and so on. I'm not going to go through it in detail. But basically, this is...
So empty list, then visited is an empty set, new, we define a new function. Wait, you can scroll in full screen? That's crazy. Am I the only one who didn't know that? You can scroll when you have a video in full screen. Wow. Surely this wasn't possible a few years ago. Alright, anyways. Build topo v. If v is not in visited that add v for child in v pref. Topo append build topo. It's pretty simple, honestly. Like, you know, now that we've read the explanation on complexity. Okay, where do we put it though? Right above this. Okay, let's do it. Topo equals empty listing. Then visited is an empty set. Why am I like starting to get into the groove right now after many hours? Def build topo v. If v is not in visited that add v for child in v. Whoa, is that brev? Really, yeah, not a. What am I doing? Build topo on child. Okay. So v would be, yes, a node or something. And then we're calling it on that. If v is not in visited, it's added to visited, and then for every child of it, it's also running through it. So it's going backwards. Yeah, I mean, pretty simple. I guess there can be more advanced topological sorts because we have pretty simple graph. Topo append v. What is, oh yeah, build topo O topo. So we're going from it's a set showing it's showing the list, but the list is going from O. This is the first, second, and we have two children. So the bias is first and then X, whatever this variable. But then why is the zeros? Whatever.
Is what builds a topological graph. We maintain a set of visited nodes, and then we are going through, starting at some root node, which for us is O. That's where we want to start the topological sort. And starting at O, we go through all of its children, and we need to lay them out from left to right. And basically, this starts at O. If it's not visited, then it marks it as visited, and then it iterates through all of its children and calls build topological on them. And then after it's gone through all the children, it adds itself. So basically, this node that we're going to call it on, like say O, is only going to add itself to the topo list after all of the children have been processed. And that's how this function is guaranteed.
Oh. Okay. Now that makes way more sense. This adds itself last. This adds itself second last. This adds itself third last. 6. Zero. Yes. Data 0, data still doesn't make sense. Why the -6 is high up and the dependency rerun it.
Guaranteeing that you're only going to be in the list once all your children are in the list, and that's the invariant thing.
Maybe compare it. Maybe I have to incorrectly implemented. I don't know. No, correct.
That is being maintained. So if we build topo on O and then inspect this list, we're going to see that it ordered our value objects. And the last one is the value of 0.707, which is the output. So this is O.
Oh, it is.
And then this is N. And then all the other nodes get laid out before it. So that builds the topological graph. And really what we're doing now is we're just calling dot_backward on all of the nodes in a topological order. So if we just reset the gradients, they're all 0. What did we do? We started by setting O.grad. So that builds the topological graph. And really what we're doing now is we're just calling dot_backward on all of the nodes in a topological order.
But we're not even using underscore back.
So if we just reset the gradients, they're all 0. What did we do? We started by setting.
Okay, this is resetting all gradients. Drawing.
O.grad to be 1. That's the base case. Then we built the topological order. And then we went for node in reversed of topo. Now, in the reverse order, because this list goes from, we need to go through it in reversed order. So starting at O, node dot backward. And this should be it. There we go. Those are the correct results.
O.grad equals 1.0. Then we copied part. And we do the backward for node in reversed topo. Node that. Let's quickly do an optic check. We have 1, 0.5, 0.5, 0.5, 0.5, and then grad is 0.5, grad is 0. Yeah, this looks to be correct. Yes. Check.
Derivatives. Finally,
Yeah. Nice. I mean, it's not the same visual. I don't know why. Maybe Matplotlib updated the library since he recorded it almost exactly 2 years ago. But yeah.
we are going to hide this functionality. So I'm going to copy this, and we're going to hide it inside the value class because we don't want to have all that code lying around. So instead of an underscore backward, we're now going to define an actual backward. So that's backward without the underscore. And that's going to do all the stuff that we just derived.
Nice. Control X, Control MD. Scroll back up to our class here, under the tangent. Def backward. Self. Boom, paste. Have to be careful here with the indentation.
So let me just clean this up a little bit. So we're first going to build a topological graph.
Interesting. So we do the O right here before we do the first call.
Starting at self. So build topo of self. We'll populate the topological order into the topo list, which is a local variable. Then we set self.grad to be 1. And then for each node in the reverse.
Yeah, O doesn't mean anything here.
First list. So starting at us and going to all the children, underscore backward. And that should be it. So
why is this the same? It's so tilting. Like, why is that in the same cell as the value one? Anyways.
Save. Come down here. Redefine. Okay, all the grads are 0. And now what we can do is.
Okay, we run this. Then we redraw. All the grads are 0 indeed. Oh wait, they should be here. What am I saying? Run this, run this. All the grads are 0 indeed.
Is O dot backward without the underscore, and
so O dot backward. Redraw. Beautiful. And programming is amazing. I mean, can't argue with that.
there we go. And that's backpropagation, at least for one neuron. Now, we shouldn't be too happy with ourselves, actually, because we have a bad bug. And we have not surfaced the bug because of some specific conditions that we have to think about right now. So here's the simplest case that shows the bug. Say I create a single node A, and then I create a B that is A plus A, and then I call backward. So what's going to happen is A is 3, and then B is A plus A. So there's 2 arrows on top of each other here. Then we can see that B is, of course, the forward pass works. B is just A plus A, which is 6. But the gradient here is not actually correct, that we calculated automatically. And that's because, of course, just doing calculus in your head, the derivative of B with respect to A should be 2. 1 plus 1. It's not 1. Intuitively, what's happening here, right? So B is the result of A plus A, and then we call backward on it. So let's go up and see what that does. B is the result of addition, so out is B. And then when we call backward, what happened is self.grad was set to 1, and then other.grad was set to 1. But because we're doing A plus A, self and other are actually the exact same object. So we are overriding the gradient. We are setting it to 1, and then we are setting it again to 1. And that's why it stays at 1. So that's a problem. There's another way to see this in a little bit more complicated expression. So here we have A and B, and then D will be the multiplication of the 2, and E will be the addition of the 2. And then we multiply E times D to get F, and then we call it F dot backward. And these gradients, if you check, will be incorrect. So fundamentally what's happening here, again, is basically we're going to see an issue anytime we use a variable more than once. Until now, in these expressions above, every variable is used exactly once, so we didn't see the issue. But here, if a variable is used more than once, what's going to happen during backward pass? We're backpropagating from F to E to D, so far so good, but now E calls it backward, and it deposits its gradients to A and B, but then we come back to D and call backward, and it overwrites those gradients at A and B.
Yeah, I mean, this is one of those bugs I feel like you would not spot visually until, you know, you actually run into it. This is like the bad type of bug that, you know, can stay in the code for a long time until later, and then you're like, why is this causing issues? And it's like something you made a few months ago.
So that's obviously a problem. And the solution here, if you look at the multivariate case of the chain rule and its generalization there, the solution there is basically that we have to accumulate these gradients. These gradients add. And so instead of setting those gradients, we can simply do plus equals. We need to accumulate those gradients. Plus equals, plus equals, plus equals, plus equals.
Okay. You're not like hard setting the variable, you're like adding it. So it cannot be overridden because you're just adding on everywhere plus equals. Why is this impossible to select? Where else? Add multiply.
Plus equals. Plus equals.
Oh yeah, in the 10H.
And this will be okay, remember, because we are initializing them at 0. So they start at 0, and then any contribution that flows backwards will simply add. So now if we redefine this one,
Okay, I'm going to copy the code from this. We have the correct number, correct answer 2.
because the plus equals, this now works. Because a.grad started at 0, and when we call b.backward, we deposit 1, and then we deposit 1 again, and now this is 2, which is correct. And here, this will also work, and we'll get correct gradients. Because when we call e.backward, we will deposit the gradients from this branch, and then we get to d.backward, it will deposit its own gradients. And then those gradients simply add on top of each other. And so we just accumulate those gradients, and that fixes the issue. Okay, now before we move on, let me actually do a bit of cleanup here and delete some of this intermediate work. So we're not going to need any of this now that we've derived all of it.
Okay, name.
We are going to keep this because
Even this.
I want to come back to it. Delete the 10H.
I'm going to be real careful here because
Delete our modeling example.
we want to delete stuff that we need. I mean, obviously, there's a way to get it. The version history. Revision history.
Delete the step. H. Delete our modeling example. Delete the step.
I don't think I know the keyboard shortcut though. What is the Google Colab keyboard shortcuts that simply select the cell above or below? Not even move cursor there. Select cell as a whole. Control M. What? Oh, Control M K, Control M J. Okay, so here Control M K. Oh. Wait, is that correct? What is going on? I'm here, Control M K. And I'm here, Control M K. It's kind of weird though. Okay. Control M J. Control M K. Doesn't work. It skips this one completely. Maybe because we didn't run it. Control M J. Control M K. Control M K. This does not work at all.
Delete this. Keep this because I want to come back to it. Delete the 10H. Delete our modeling example. Delete the step. Delete this.
This we keep. What do we keep? What do we delete, Andrej?
Delete our modeling example. Become derived some of this intermediate work. So we're not going to need any of this now that we've derived all of it. We are going to keep.
Wait a minute. This graph, digraph. Why is it?
Keep this because I want to come back to it. Delete the 10H. delete our motivating example, delete the step, delete this, keep the code that draws, and then delete this example and leave behind only the definition of value.
Oh yeah, this is what I wanted to do actually. Okay, so do we keep this? Wait, does he have a different order?
And the 10H, delete our motivating.
He has this below. Oh, it's moving the cell. I messed up the cell order, Jesus Christ. Oh my god. Completely messed things up.
Example, delete the step, delete this, keep the code that draws.
And we delete all of this.
And now let's come back to this nonlinearity here that we implemented to 10H. Now I told you that we could have broken down 10H into its explicit atoms in terms of other expressions if we had the exp function. So if you remember, 10H is defined like this, and we chose to develop 10H as a single function, and we can do that because we know its derivative and we can backpropagate through it. But we can also break down 10H into and express it as a function of exp. And I would like to do that now because I want to prove to you that you get all the same results and all the same gradients, but also because it forces us to implement a few more expressions. It forces us to do exponentiation, addition, subtraction, division, and things like that. And I think it's a good exercise to go through a few more of these. Okay, so let's scroll up to the definition of value. And here, one thing that we currently can't do is we can do like a value of, say, 2.0, but we can't do, you know, here, for example, we want to add a constant 1, and we can't do something like this. And we can't do it because it says int object has no attribute.
So we would have to do a.data plus 1.
Data. That's because a plus 1 comes right here to add, and then other is the integer 1. And then here Python is trying to access 1.data, and that's not a thing. And that's because basically 1 is not a value object, and we only have addition for value objects. So as a matter of convenience, so that we can create expressions like this and make them make sense, we can simply do something like this. Basically, we let other alone if other is an instance of value.
Other equals other if is instance of value, else value other.
But if it's not an instance of value, we're going to assume that it's a number, like an integer or a float, and we're going to simply wrap it in value.
Oh, okay.
And then other will just become value of.
It's kind of nice. Let's do it. Other equals other if is instance other value, else value other. So now if I run this, well, we should run all. But if I run this, Control MB, and do a equals value 3.0, a plus 1, works. It works, nice.
Other, and then other will have a data attribute, and this should work. So if I just say this, redefine value, then this should work. There we go. Okay, and now let's do the exact same thing for multiply, because we can't do something like this, again, for the exact same reason. So we just have to go to mul, and if other is not a value, then let's wrap it in value.
So literally copy paste the exact same line of code, put it into multiplication. And now we can test it. 8 times 3, so we should get 9 here. Beautiful.
Let's redefine value, and now this works. Now here's a kind of unfortunate and not obvious part. A times 2 works, we saw that, but 2 times A, is that going to work? You'd expect it to, right? But
2 times value object.
Actually, it will not. And the reason it won't is because Python doesn't know, like when you do A times 2, basically, so a times 2, Python will go and it will basically do something like a.mul of 2. That's basically what it will call. But to it, 2 times a is the same as 2.mul of a. And it doesn't,
and that's value object.
Can't multiply value. And so it's really confused about that. So instead, what happens is in Python, the way this works is you are free to define something called the rmul.
Reverse mul.
And rmul is kind of like a fallback. So if Python can't do 2 times a, it will check if by any chance a knows how to multiply 2, and that will be called into rmul. So because Python can't do 2 times a, it will check, is there an rmul in value? And because there is, it will now call that.
Very interesting. Now we're getting into the quirks of Python. It's definitely not obvious stuff. Rmul, self, other, and then so this is called when other is timed by self. So you just return self times other. Let's test it out. So obviously this works still, but 3 times a. Nice.
And what we'll do here is we will swap the order of the operands. So basically 2 times a will redirect to rmul, and rmul will basically call a times 2. And that's how that will work. So redefining now with rmul, 2 times a becomes 4. Okay, now looking at the other elements that we still need, we need to know how to exponentiate and how to divide. So let's first do the exponentiation part. We're going to introduce a single function exp here.
Define exponentiation self. X dot self data. X equals self dot data. Out equals value. Out value. Out equals value object. Math dot exponentiation x. Self empty tuple. And then exp. Okay, yeah.
And exp is going to mirror 10h in the sense that it's a single function that transforms a single scalar value and outputs a single scalar value. So we pop out the Python number, we use math.exp to exponentiate it, create a new value object, everything that we've seen before. The tricky part, of course, is how do you backpropagate through e to the x? And so here, you can potentially pause the video and think about what...
So is this logarithm? I mean, Autograd plus equal. Wait. I mean, exponentiation is root. The opposite of exponentiation is like root. It's like square root and so on. Backpropagate, we need the gradient.
Should go here. Okay, so basically, we need to know what is the local derivative of e to the x. So d by dx of e to the x is, famously, just e to the x. And we've already just calculated e to the x, and it's inside out.data. So we can do out.data times, and out.grad, that's the chain rule. So we're just chaining on to the current running grad And this is what the expression looks like. It looks a little confusing, but this is what it is, and that's the exponentiation. So redefining, we should now be able to call a dot x, and hopefully the backward pass works as well. Okay.
A dot x plus tested out. A dot x. Different value than him, so yeah. Okay. We have this. Yeah, this adds up. So backpropagation here, self dot gradient plus equals output dot data times output dot gradient if it's exponential. I still don't understand this fully, but.
And the last thing we'd like to do, of course, is we'd like to be able to divide. Now, I actually will implement something slightly more powerful than division, because division is just a special case of something a bit more powerful. So in particular, just by rearranging, if we have some kind of a b equals value of 4.0 here, we'd like to basically be able to do a divide b, and we'd like this to be able to give us 0.5. Now, division actually can be reshuffled as follows. If we have a divide b, that's actually the same as a multiplying 1 over b, and that's the same as a multiplying b to the power of -1. And so what I'd like to do instead is I'd basically like to implement the operation of x to the k for some constant k. So it's an integer or a float, and we would like to be able to differentiate this. And then as a special case, -1 will be division. And so I'm doing that just because it's more general, and yeah, you might as well do it that way. So basically what I'm saying is we can redefine division, which we will put here somewhere. Yeah, we can put it here somewhere. What I'm saying is that we can redefine division, so self-divide other, this can actually be rewritten as self times other to the power of -1.
Yeah, this is like one of those beautiful math concepts that when you understand it, it's just like you can't unsee it basically. A true diff. So another function called true diff. Let's add it. Diff, true division, self other. Return self times other to the power of -1. Like this. Okay, let's add the comment as well. Self divided by other. But then do we get an error in the reverse? Let's see. Let's see if the same problem arises, right? So we can have, let's say, 4. And let's do a divided by 2. That works. But does 8 divided by a work? No, we still have the error. So do we then implement the same fix? Let's see if the same fix works. No. Let's see. How do we fix it then?
And now, a value raised to the power of -1, we have to now define that. So so we need to implement the pow function. Where am I going to put the pow function? Maybe here somewhere. This is the skeleton for it. So this function will be called when we
Pow function above RML.
try to raise a value to some power, and other will be that power. Now, I'd like to make sure that other is only an int or a float. Usually other is some kind of a different value object, but here other will be forced to be an int or a float. Otherwise, the math won't.
Assert. Oh. I don't need to understand that. That's complexity. explain what assert does in Python. What is assert? Assert is a debugging aid that tests a condition. If the condition is true, the program continues to run. If the condition is false, program... Right. Okay, so this is basically the shortest way to do like try catch. Or try except. So basically this is the shortest way to do try catch. Not exactly. Well, assert and try catch both deal with handling unexpected situations. They serve different purposes and are used in different contexts. Purpose: assert, used for debugging and testing. It checks if a condition is true. It is an error, used for handling exceptions that might occur during program execution. Used during development, used in production. Stops the program immediately, allows the program to continue. Often disabled in production. Okay.
Work for what we're trying to achieve in this specific case. That would be a different derivative expression if we wanted other to be a value. So here we create the output value, which is just this data raised to the power of other, and other here could be, for example, -1. That's what we are hoping to achieve. And then this is the backward stub, and this is the fun part, which is what is the chain rule expression here for backpropagating through the power function, where the power is to the power of some kind of a constant. So this is the exercise, and maybe.
So it is, if it's multiplied by that constant, so it is just that constant, no? Other that value, other that data, plus equals other that data.
Here, and see if you can figure it out yourself as to what we should put here. Okay, so
because in previous cases of multiplication we always used the different values. So if it's, but it was, this is to the power, this is not multiplication. So it's multiplied by the same thing. So the same thing, okay, maybe it's self.data to the power of other. I don't know, let's see.
You can actually go here and look at derivative rules as an example. And we see lots of derivative rules that you can hopefully know from calculus. In particular, what we're looking for is the power rule, because that's telling us that if we're trying to take d by dx of x to the n, which is what we're doing here, then that is just n times x to the n minus 1, right? Okay, so that's telling us about the local derivative of this power operation. So all we want here, basically n is now other, and self.data is x. And so this now becomes other, which is n, times self.data, which is now a Python int or a float. It's not a value object. We're accessing the data attribute, raised to the power of other minus 1, or n minus 1.
Okay, I was completely off.
I can put brackets around this, but this doesn't matter because power takes precedence over multiply in Python, so that would have been okay. And that's the local derivative only, but now we have to chain it. And we chain it just simply by multiplying by Autograd. That's chain rule. And this should technically work. And we're going to find out soon. But now, if we do this, this should now work. And we get 0.5. So the forward pass works, but does the backward pass work? And I realized that we actually also have to know how to subtract. So right now, a minus b will not work. To make it work, we need one more piece of code here. And basically, this is the...
Okay, so two new functions, negative and subtract. Negative and subtract. So this just, returns self to the self times minus 1, the negative version of that value, and then subtract plus minus other. Interesting. It's defined this way. let's see why he defined it like this.
Subtraction, and the way we're going to implement subtraction is we're going to implement it by addition of a negation, and then to implement negation, we're going to multiply by -1. So just again, using the stuff we've already built and just expressing it in terms of what we have, and a minus b is now working. Okay, so now let's scroll.
Oh, because this will, you know, if this is a value object, then it probably doesn't know what to do, so then it calls this the under function, and it just multiplies by -1, and then this works. Wow.
Again to this expression here for this neuron, and let's just compute the backward pass here once we've defined O, and let's draw it. So here's the gradients for all of these leaf nodes for this two-dimensional neuron that has a 10H that we've seen before. So now what and a minus b is now working. Okay, so now let's scroll again to this expression here for this neuron, and let's just compute the backward pass here once we've defined O, and let's draw it. Just compute the backward pass here once we've defined O, and let's draw it.
Okay. This still doesn't work though, but let's do a divided by 2. This does work, okay. I don't know if he fixes that later or not. Oh, that backward. Run this and run this, and we get the gradients.
So here's the gradients for all of these leaf nodes for this two-dimensional neuron that has a 10H that we've seen before. So now what I'd like to do is I'd like to break up this 10H into this expression here. So let me copy paste this here. And now instead of, we'll preserve the label, and we will change how we define O. So in particular, we're going to implement this formula here. So we need e to the 2x minus 1 over e to the x plus 1. So e to the 2x, we need to take 2 times n, and we need to exponentiate it. That's e to the 2x. And then because we're using it twice, let's create an intermediate variable, e, and then define O as e plus 1 over e minus 1 over e plus 1. E minus 1 over e plus 1. And that should be it. And then we should be able to draw dot of O. So
honestly, this makes me realize just how interconnected high-level programming and high-level math is. Because like you can do low-level programming with basically zero math, but like the higher you go, the more connected they are. It's kind of fascinating.
Now, before I run this, what do we expect to see? Number one, we're expecting to see a much longer graph here because we've broken up 10H into a bunch of other operations. But those operations are mathematically equivalent. And so what we're expecting to see is, number one, the same result here. So the forward pass works. And number two, because of that mathematical equivalence, we expect to see the same backward pass and the same gradients on these leaf nodes. So these gradients should be identical. So let's run this. So number one, let's verify that instead of a single 10H node, we have now exp, and we have plus, we have times -1. This is the division. And we end up with the same forward pass here. And then the gradients, we have to be careful because they're in slightly different order potentially. The gradients for W2, X2 should be 0 and 0.5. W2 and X2 are 0 and 0.5. And W1, X1 are 1 and -1.5. 1 and -1.5. So that means that...
So let me actually implement this part. So we do a line splitter. Oh, that 10H. Draw dot O. We split this. And instead of doing this, we define the e variable 2 times n exponentiated, 2 times n exp, and then O e minus 1 divided, okay. equals t minus 1 divided by t plus 1. Let's rerun. We got an error. Minus. Why doesn't minus work? Oh wait, I think we didn't run this. Oops. We forgot to rerun everything. Yeah? Works. Nice.
Both our forward passes and backward passes were correct, because this turned out to be equivalent to 10H before. And so the reason I wanted to go through this exercise is, number one, we got to practice a few more operations and writing more backwards passes. And number two, I wanted to illustrate the point that the level at which you implement your operations is totally up to you. You can implement backward passes for tiny expressions like a single individual plus or a single times, or you can implement them for, say, 10H, which is a kind of a, potentially you can see it as a composite operation because it's made up of all these more atomic operations. But really all of this is kind of like a fake concept. All that matters is we have some kind of inputs and some kind of an output, and this output is a function of the inputs in some way. And as long as you can do forward pass and the backward pass of that little operation, it doesn't matter what that operation is and how composite it is.
It's kind of a big realization. Like, all you need to know is the derivative of that function, and you can use the world's most complex function.
It is. If you can write the local gradients, you can chain the gradient and you can continue backpropagation. So the design of what those functions are is completely up to you. So now I would like to show you how you can do the exact same thing, but using a modern deep neural network library, like, for example, PyTorch, which I've roughly modeled Micrograd by.
I just watched the recent PyTorch documentary, and I highly recommend it. It's like 40 minutes or something, but it shows the history of development of PyTorch and honestly makes me want to learn it even more.
So now I would like to show you how you can do the exact same thing, but using a modern deep neural network library, like, for example, PyTorch, which I've roughly modeled Micrograd by. And so PyTorch is something you would use in production, and I'll show you how you can do the exact same thing, but in PyTorch API. So I'm just going to copy paste it in and walk you through it a little bit. This is what it looks like. So we're going to import PyTorch, and then we need to define these value objects like we have here. Now, Micrograd is a scalar valued engine, so we only have scalar values like 2.0. But in PyTorch, everything is based around tensors. And like I mentioned, tensors are just n-dimensional arrays of scalars. So that's why things get a little bit more complicated here. I just need a scalar valued tensor, a tensor with just a single element. But by default, when you work with PyTorch, you would use more complicated tensors like this. So if I import PyTorch, then I can create tensors like this. And this tensor, for example, is a 2x3 array of scalars in a single compact representation. So we can check its shape. We see that it's a 2x3 array, and so on. So this is usually what you would work with in the actual libraries.
So obviously the libraries make it much easier for us to build the advanced neural networks so that we don't have to code everything from scratch, such as we do here in Micrograd. However, the benefit of coding everything from scratch is that actually you understand every single element of it. If you're just, only using libraries and never trying to build anything from scratch, then you don't develop that deep understanding required for mastery.
So here I'm creating a tensor that has only a single element, 2.0. And then I'm casting it to be double, because Python is by default using double precision for its floating point numbers. So I'd like everything to be identical. By default, the data type of these tensors will be float 32. So it's only using a single precision float. So I'm casting it to double so that we have float 64 just like in Python. So I'm casting to double, and then we get something similar to value of 2. The next thing I have to do is, because these are leaf nodes, by default, PyTorch assumes that they do not require...
This is interesting, like, at certain levels, it's just like knowledge and nuances of the language model, of the programming language, such as, Andrej saying that Python using float 64, if you don't know that, you wouldn't know to use that double in the, defining the tensor with PyTorch. So like there's literally like thousands of these micro informations of knowledge that compound and lead to somebody being so good, such as Karpathy.
Require gradients. So I need to explicitly say that all of these nodes require gradients. Okay, so this is going to construct scalar valued one element tensors. Make sure that PyTorch knows that they require gradients. Now, by default, these are set to false, by the way, because of efficiency reasons, because usually you would not want gradients for leaf nodes, like the inputs to the network. And this is just trying to be efficient in the most common cases. So once we've defined all of our values in PyTorch land, we can perform arithmetic just like we can here in Micrograd land. So this would just work. And then there's a torch.tanh also. And what we get back is a tensor again, and we can, just like in Micrograd, it's got a data attribute and it's got grad attributes. So these tensor objects, just like in Micrograd, have a .data and a .grad. And the only difference here is that we need to call a .item because otherwise PyTorch .item basically takes a single tensor of one element and it just returns that element, stripping out the tensor. So let me just run this, and hopefully we are going to get, this is going to print the forward pass, which is 0.707, and this will be the gradients, which hopefully are 0.50, negative 1.5, and 1. So if we just run this, there we go, 0.7, so the forward pass agrees, and then 0.50, negative 1.5, and 1. So PyTorch agrees with us. And just to show you here, basically, here's a tensor with a single element, and it's a double, and we can call .item on it to just get the single number out.
Wait, .item and .data item will produce the same result here in PyTorch.
So that's what item does. And O is a tensor object, like I mentioned, and it's got a backward function, just like we've implemented. And then all of these also have a .grad.
So this is very good, thinking ahead by Karpathy, like naming everything in Micrograd the same way it's named in PyTorch, so that when we learn it here, when we actually learn PyTorch, which is, as he says, the thing that you would use in production, you already know the naming, you already know the syntax basically, because, you've used it with Micrograd. Very nice. He's preparing us for the next levels.
So like x2, for example, has a grad, and it's a tensor, and we can pop out the individual number with .item. So basically, Torch can do what we do.
Let's do this part. Import Torch. And then this piece of code. Okay, let's run this. And we got the correct O value, O data, 0.7. And then these are for the gradient on the backward pass for the input leaf nodes. 0.5, yeah, adds up. Very nice.
In Micrograd as a special case when your tensors are all single element tensors. But the big deal with PyTorch is that everything is significantly more efficient because we are working with these tensor objects, and we can do lots of operations in parallel on all of these tensors. But otherwise, what we've built very much agrees with the API of PyTorch. Okay, so now that we have some machinery to build out pretty complicated mathematical expressions, we can also start building out neural nets. And as I mentioned, neural nets are just a specific class of mathematical expressions. So we're going to start building out a neural net piece by piece, and eventually we'll build out a two-layer, multi-layer perceptron, as it's called, and I'll show you exactly what that means.
Wait, wasn't that like Frank Rosenbaum who invented perceptrons? Who invented perceptrons? Frank Rosenblatt, okay. The perceptron was invented by Warren McCullough and Walter Pitts in 1943. However, the development and popularization of the perceptron as a machine learning algorithm is largely attributed to Frank Rosenblatt, who made significant contributions to the field in the late 1950s and early 1960s. Wow, he'd only died at age of 43. But yeah, Frank was cooking. Frank was cooking the perceptrons. 60 years too soon. That's crazy. He was literally... This is just pure luck, like when you're born. He was working on the right thing, but he was born too soon. Man. So unlucky. Like, all of us are so lucky to be born in the exact time to witness the creation of, you know, the explosion of AI at the very least, and hopefully as well the creation of AGI, and potentially even ASI. Some people were 60 years too early working on the field when nobody believed them, when it wasn't obvious at all that AI was going to work.
Let's start with a single individual neuron. We've implemented one here, but here I'm going to implement one that also subscribes to the PyTorch API in how it designs its neural network modules. So just like we saw that we can like match the API of PyTorch on the Autograd side, we're going to try to do that on the neural network modules. So here's class neuron. And just for the sake of efficiency, I'm going to copy paste some sections that are relatively straightforward. So the constructor will take number of inputs to this neuron, which is how many inputs come to a neuron. So this one, for example, has 3 inputs. And then it's going to create a weight that is some random number between -1 and 1 for every one of those inputs, and a bias that controls the overall trigger happiness of this neuron. And then...
Okay, let's actually code this out. Class neuron. Dunder method, the constructor, self, number of inputs, and in, yeah. Self.w equals, this is the weight. And now we're gonna do a list. Okay. Value random.uniform -1, 1. Or, and this is, you know, using underscore is just a filler object, no need to name it, or, you know, or like item, for every item or element in range number of inputs. I guess for every input, yeah, in range of number of inputs. And then we declare the bias, self, that bias equals value object of random.uniform -1, 1.
Then we're going to implement a def___ call of self and x, some input x. And really what we want to do here is w times x plus b, where w times x here is a dot product specifically. Now, if you haven't seen call, let me just return 0.0 here from now. The way this works now is we can have an x, which is say like 2.0, 3.0. Then we can initialize a neuron that is 2-dimensional, because these are 2 numbers. And then we can feed those 2 numbers into that neuron to get an output. And so when you use this notation, n of x, Python will use call. So currently, call just returns 0.0. Now, we'd like to...
Another dunder method that we haven't used yet, call. So that's, you know, when you use the neuron of x.
Actually,
in this case, x is a simple list.
Forward pass of this neuron instead. So what we're going to do here first is we need to basically multiply all of the elements of w with all of the elements of x pairwise. We need to multiply them. So the first thing...
So that's going to be nested for loops. At least that's my prediction.
What we're going to do is we're going to zip up salta w and x. And in Python, zip takes 2 iterators, and it creates a new iterator that iterates over the tuples of their corresponding entries. So for example, just to show you, we can print this list and still return 0.0 here.
Yeah, I don't think that's how you do print statements in Python.
Sorry. I mean, so
his brain is going too fast, so some like basic syntax, forget it. He's already, working on the next piece of code.
You see that these W's are paired up with the X's, W with X. And now what we want to do is for Wi xi in, we want to multiply Wi times xi, and then we want to sum all of that together to come up with an activation.
That's amazing.
And add also self.b on top.
I mean, obviously there are like lines of code that are way more advanced than this, but for most people this would be a pretty complicated line of code, right? But Karpathy just like reverse engineered it in 2 seconds, and he has it written. Declaring a new variable, assigning to it the sum of multiplications wixy for wixi in the zip. So like as we see, the tuples of the random, number from -1 to 1, and then x, which is whatever number we're feeding in through the call method. And then we also need to add the bias on top. I mean, this is basically this equation, right? Which is written out in code.
So that's the raw activation. And then, of course, we need to pass that through a nonlinearity. So what we're going to be returning is act.10h. And here's out. So now we see that we are getting some outputs. And we get a different output from a neuron each time because we are initializing different weights and biases. And then to be a bit more efficient here, actually.
This is pretty nice. This is pretty cool, not gonna lie. Okay, and now let's test it out with, random x and random n. Neuron. Oh no, just the list. N is the neuron. Three 3.0, 1.0, n of x. Random is not defined. We didn't import random. Okay, and now every time it returns a different value. Yep.
Sum, by the way, takes a second optional parameter, which is the start. And by default, the start is 0. So these elements of this sum will be added on top of 0 to begin with. But actually,
we can do -1.
We can just start with self.b.
Oh, with the bias.
And then we just have an expression like this. And then the generator expression here must be parenthesized in Python. There we go.
Interesting. So this is another extra knowledge of the, built-in methods and functions into Python. I didn't know that sum method took a second parameter, but apparently it does, and it lets us simplify the code even further.
Yep, so now we can forward a single neuron. Next up, we're going to define a layer of neurons. So here we have a schematic for a MLP. So we see that these MLPs, each layer, this is one layer, has actually a number of neurons, and they're not connected to each other, but all of them are fully connected to the input. So what is a layer of neurons? It's just a set of neurons evaluated independently. So in the interest of time, I'm going to do something fairly straightforward here. It's literally a layer is just a list of neurons, and then how.
So let's define a new class. Again, constructor init and call the under method.
How many neurons do we have? We take that as an input argument here. How many neurons do you want in your layer? Number of outputs in this layer. And so we just initialize completely independent neurons with this given dimensionality. And when we call on it, we just independently evaluate them. So now instead of a neuron, we can make a layer of neurons. They are two-dimensional neurons, and let's have 3 of them. And now we see that we have 3 independent evaluations of 3 different neurons, right? Okay, and finally, let's complete this picture and define an entire multi-layer perceptron, or MLP. And as we can see here, in an MLP, these layers just feed into each other sequentially. So let's come here, and I'm just going to copy the code here in the interest of time. So an MLP is very similar.
Okay, let's see if it was still Frank Rosenblatt who invented multi-layer perceptrons. And what about MLPs? Multi-layer. Who invented and popularized those? Yeah, this is so nice. I mean, I know I said it multiple times, but the pro surge in perplexity. Amazing to watch. So Frank Rosenblatt's early work. Okay, so he invented the single layer perceptron in 1957. Actually worked on multi-layer models as well. Yeah, I mean, they were so limited by hardware, it's just like, it was so hard to do anything at that time, given how bad computers were. Revival. The real breakthrough and popularization of multi-level perceptrons came in the 1980s, primarily through David Ramonhold, Geoffrey Hinton, shout out, Ronald Williams. Their 1986 paper, Learning Internal Representations by Error Propagation, was pivotal. So this was basically the backpropagation paper, I guess. They introduced nonlinear but differentiable transfer functions, avoiding the problem of step functions used in earlier perceptrons, an effective training algorithm for multi-layer networks, backpropagation.
We're taking the number of inputs as before, but now instead of taking a single N-out, which is the number of neurons in a single layer, we're going to take a list of N-outs, and this list defines the sizes of all the layers that we want in our MLP.
Let's implement this.
So here we just put them all together and then iterate over consecutive pairs of these sizes and create layer objects for them. And then in the call function, we are just calling them sequentially. So that's an MLP really. And let's actually re-implement this picture. So we want 3 input neurons and then 2 layers of 4 and an output unit. So we want a 3-dimensional input. Say this is an example input. We want 3 inputs into 2 layers of 4 and 1 output. And this, of course, is an MLP. And there we go. That's a forward pass of an MLP. To make this a little bit nicer, you see how we have just a single element, but it's wrapped in a list, because layer always returns lists. So for convenience, return outs at 0 if len outs is exactly a single element, else return full list. And this will allow us to just get a single value out at the last layer that only.
Even like simple lines of code like this are so nice. Like just having the, internalization of Python to be able to solve this issue so quickly just saves so much time. Like somebody maybe on my level would spend maybe a minute or 2 minutes writing this out or like figuring out that this is the simplest way to do this, but like Karpathy sees it instantly. Like so amazing, man.
Only has a single neuron. And finally, we should be able to draw dots of n of x. And as you might imagine, these expressions are now getting relatively involved. So this is an entire MLP that we're defining now, all the way until a single output. Okay? And so obviously you would never differentiate on pen and paper these expressions, but with Micrograd
if you remember, we actually built this function, you know, draw dot. Obviously, we're using the matplotlib library to help us out, but it's pretty amazing what this function can do.
For grad, we will be able to backpropagate all the way through this and backpropagate into these weights of all these neurons. So let's see how that works. Okay, so let's create ourselves a very simple example data set here. So this data set has 4 examples. And so we have 4 possible inputs into the neural net. And we have 4 desired targets. So we'd like the neural net to assign or output 1.0 when it's fed this example, -1 when it's fed these examples, and 1 when it's fed this example. So it's a very simple binary classifier neural net basically that we would like here. Now let's think what the neural net currently thinks about these 4 examples. We can just get their predictions. Basically, we can just call n of x for x in x's, and then we can print. So these are the outputs of the neural net on those 4 examples. So the first one is 0.91, but we like it to be 1. So we should push this one higher. This one we want to be.
Okay, so will we do now basically the gradient descent where it's adjusting the weights to get these outputs? Because that's, to me, is the coolest part.
Be higher. This one says 0.88, and we want this to be -1. This is 0.88, we want it to be -1. And this one is 0.88, we want it to be 1. So how do we make the neural net, and how do we tune the weights to better predict the desired targets?
So we adjust the gradient based on the influence of the output. Right? Because when we did it manually, we saw what each of the nodes, you know, each of the nodes has a gradient, either positive or negative, and you can see how it influences the final output. So in order to reach these desired targets, we just work with the gradient of each node and tune it based on its current, you know, value.
And the trick used in deep learning to achieve this is to calculate a single number that somehow measures the total performance of your neural net. And we call this single number the loss.
Loss, yeah, loss function.
So the loss first is a single number that we're going to define that basically measures how well the neural net is performing. Right now we have the intuitive sense that it's not performing very well because we're not very much close to this. So the loss will be high, and we'll want to minimize the loss. So in particular in this case,
basically the loss will be calculated as a difference between the current outputs and the desired outputs.
What we're going to do is we're going to implement the mean squared error loss. So what this is doing is we're going to basically iterate for y ground truth and y output in zip of y's and y pred. So we're going to pair up the ground truths with the predictions, and this zip iterates over tuples of them. And for each y ground truth and y output, we're going to subtract them and square them. So let's first see what these losses are. These are individual loss components. And so basically for each one of the 4, we are taking the prediction and the ground truth, we are subtracting them and squaring them.
Oh yeah, so you can see like here, the ones that need to be -1 but are 0.88, the loss is very high because they're completely off. But these ones that are relatively close, like, you know, 0.91 is kind of close to 1.0. 0.88 is not as close, but still very close. So the loss is very low.
So because this one is so close to its target, 0.91 is almost 1, subtracting them gives a very small number. So here we would get like a...
I wonder why we do the squared, so that, you know, we can see the bad errors even more potent.
-0.1, and then squaring it just makes sure that regardless of whether we are more negative or more positive, we always get a positive number.
Never mind, it's even better, even smarter reason to square it, because, you know, -4 times -4, in other words, -4 squared is 16. So any number that we get, no matter positive or negative, we get a positive at the end. So yeah, that's even a better reason to square it.
Instead of squaring, we could also take, for example, the absolute value. We need to discard the sign. And so you see that the expression is ranged so that you only get 0 exactly when y out is equal to y ground truth. When those two are equal, so your prediction is exactly the target, you are going to get 0. And if your prediction is not the target, you are going to get some other number. So here, for example, we are way off. And so that's why the loss is quite high. And the more off we are, the greater the loss will be. So we don't want high loss, we want low loss. And so the final loss here will be just the sum of all of these numbers. So you see that this should be 0 roughly.
Wow, okay, so again, here the squaring has another like purpose, because it basically shows us, once it's all summed up into a single number, it shows us better like whether there's like one neuron or one weight that's completely off, the loss would still be kind of high. So it like better represents the overall performance of the network.
Roughly plus 0 roughly, but plus 7. So loss should be about 7 here. And now we want to minimize the loss. We want the loss to be low, because if loss is low, then every one of the predictions is equal to its target. So the loss, the lowest it can be is 0, and the greater it is, the worse off the neural net is predicting. So now, of course, if we do loss step backward, something magical happened when I hit enter. And the magical thing, of course, that happened is that we can look at n.layers.neuron, n.layers at, say, like the first layer, that neurons at 0. Because remember that MLP has the layers, which is a list, and each layer has neurons, which is a list, and that gives us an individual.
One thing I would say is that, you know, as we're getting more advanced, instead of Karpathy speeding up through the concepts, I would like him to slow down and like dive deeper into the code. But I mean, already this being a free YouTube video is just a blessing, so I cannot even complain.
Neuron, and then it's got some weights. And so we can, for example, look at the weights at 0. Oops, it's not called weights, it's called W. And that's a value, but now this value also has a grad because of the backward pass. And so we see that because this gradient here on this particular weight of this particular neuron of this particular layer is negative, we see that its influence on the loss is also negative. So slightly increasing this particular weight of this neuron of this layer would make the loss go down. And we actually have this information for...
So this is how neural networks are being trained. You adjust the weights to get a lower loss. And obviously the more hardware you have, the faster it is. But the more layers are there in the neural networks, and the more parameters and more weights, the slower it takes. So, you know, you kind of fight with more hardware against bigger neural networks, but obviously the result is the smartest LLMs in the world.
For every single one of our neurons and all of their parameters. Actually, it's worth looking at also the draw dot of loss, by the way. So previously we looked at the draw dot of a single neuron forward pass, and that was already a large expression. But what is this expression? We actually forwarded every one of those 4 examples, and then we have the loss on top of them with the mean squared error. And so this is a really massive graph. Because this graph that we've built up now, oh my gosh, this graph that we've built up now, which is kind of excessive.
So this is the multi-layer perceptron.
It's excessive because it has 4 forward passes of a neural net for every one of the examples. And then it has the loss on top, and it ends with the value of the loss, which was 7.12. And this loss will now backpropagate through all the 4 forward passes, all the way through just every single intermediate.
And what's amazing is that compared to the most advanced AI models, you know, GPT-4o, Claude 3.5 Sonnet, this is still nothing. But you can see how we went from an empty Jupyter notebook. We went from no code to having something like this. Obviously, took Karpathy a few hours, but, you know, It's pretty crazy how you can see something this complicated and still realize that this is like level 2 maybe out of level 10 on the deep learning scale. Wild.
Value of the neural net, all the way back to, of course, the parameters of the weights, which are the input. So these weight parameters here are inputs to this neural net, and these numbers here, these scalars, are inputs to the neural net. So if we went around here, we will probably find some of these examples, this 1.0, potentially maybe this 1.0, or some of the others, and you'll see that they all have gradients as well. The thing is, these gradients on the input data are not that useful to us. And that's because the input data is assumed to be not changeable. It's a given to the problem. And so it's a fixed input. We're not going to be changing it or messing with it.
Oh, so this is basically like the training data in, large LLMs. And then what you don't care about the gradients of the training data, you care about the gradients of the neurons and of the weights in the hidden layers of the network. I mean, you remember how it was like, neural network input layers. Yeah, beautiful. So the input layers, we don't care about the gradients of these. We care about gradients of the hidden layers. We tune those, we train those, we adjust those so that our output is, the loss of our output is as low as possible. Nice.
Even though we do have gradients for it. But some of these gradients here will be for the neural network parameters, the W's and the B's. And those of course we want to change. Okay, so now we're going to want some convenience code to gather up all of the parameters of the neural net so that we can operate on all of them simultaneously. And every one of them, we will nudge a tiny amount based on the gradient information. So let's collect the parameters of the neural net all in one array. So let's create a parameters of self that just returns self.w, which is a list, concatenated with a list of self.b. So this will just return a list. List plus list just gives you a list. So that's parameters of Neuron. And I'm calling it this way because also PyTorch has a parameters on every single NN module. And
see, as I said, he's just making it for us easier to transfer to PyTorch in the future, since we're already watching this video.
It does exactly what we're doing here. It just returns the parameter tensors. For us, it's the parameter scalars. Now, layer is also a module, so
let me implement the parameters. Return self.weight plus self.bias in a list.
It will have parameters, self. And basically what we want to do here is something like this, like params is here, and then for neuron in self.neurons, we want to get neuron.parameters, and we want
append them
to params.extend.
Extend?
Right, so these are the parameters of this neuron, and then we want to put them on top of params. So params.extend of p's.
Okay, why not append?
And then we want to return params.
Okay, I need to ask Perplexity because okay, this is fascinating though. I would have guessed it was append, but it's extend. I need to know when extend is used. What am I doing? Not a function. PS equals neuron parameters. This is, man, I'm like so rusty, it's kinda disgusting. Params.extend PS. Extend. So what does the extend function method does what does the extend method do on lists? That's what I need to know. Okay. I'm gonna paste this into Perplexity. Why are we using extend in this code instead of append? What does do compared to? Yeah, I need to. Again, this is probably something I should already know, but let's see. Great question. Let's clarify the difference between extend and append, and why extend is more appropriate in this context. Append adds a single element to the end of the list. The element is added as is, even if it's an iterable. Extend adds all elements from an iterable, like a list, to the end of the list. It extends the list by adding each element of the iterable individually. Neuron.parameters. Oh yeah. So here, neuron.parameters obviously refers to this. And this is lists. We're concatenating two lists, which will output one list. And we don't want to just append a single element to the end of the list, because that would add the list itself. We want the elements from our list to be added, not the list, right? So let's say you have a box. You don't want the entire box to be added. You want what's inside of the box, so that it's a smooth list, right? Because if you have a main list of numbers and you're just trying to append a new list, it'll be a list of 1, 2, 3, 4, and then a list, and then the numbers. But you don't want 1, 2, 3, 4 and a list. You want 1, 2, 3, 4, 5, 6, 7, 8. So you need to extract the elements from the list and extend those. Nice.
So this is way too much code. So actually there's a way to simplify this, which is return P for neuron in self.neurons for P in neuron.parameters. So it's a single list comprehension. In Python, you can sort of nest them like this, and you can then create the desired array. So these are identical. We can take this out.
Very nice. P parameter for neuron in self.neurons for parameter in neuron.parameters. Wow. List comprehensions, man. Knowing them is can save you so many lines of code. Kind of crazy.
And then let's do the same here. Def parameters self, and return a parameter for layer in self.layers for P in layer.parameters. And that should be good.
Even having that intuition, that should be good. That takes thousands of hours to develop.
Now let me pop out this so we don't re-initialize our network, because we need to and that should be good. Now let me pop out this so we don't re-initialize our
Oh, I already have it. One step ahead. Not really.
network, because we need to re-initialize our... Okay, so unfortunately we will have to probably reinitialize the network because we just add functionality. Because this class, of course, I want to get all the n.dot parameters, but that's not going to work because this is the old class. Okay, so unfortunately we do have to reinitialize the network, which will change some of the numbers. But let me do that so that we pick up the new API. We can now do n.dot parameters. And these are all the weights and biases inside the entire neural net. So in total, this MLP has 41 parameters.
Nice.
And
41 parameters in comparison. GPT-4 has like 1.8 trillion. So, you know, what we've built here, probably not on the same intelligence level, but hey, 41 is better than 0.
And now we'll be able to change them. If we recalculate the loss here, we see that unfortunately we have slightly different predictions and slightly different loss, but that's okay. Okay, so we see that this neuron's gradient is slightly negative. We can also look at its data right now, which is 0.85. So this is the current value of this neuron, and this is its gradient on the loss. So what we want to do now is we want to iterate for every p in n dot parameters. So for all the 41 parameters of this neural net, we actually want to change p dot data slightly according to the gradient information.
In the direction of the gradient to minimize the loss.
Okay, so dot 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 to do here. But this will be basically a tiny update in this gradient descent scheme.
Okay, the question is how much? Like how much we change the data. Plus equals. We could do like a simple if statement, like depending on, you know, if gradient is less than 0 or more than 0. But I think there is probably a more elegant solution coming.
And gradient descent, we are thinking of the gradient as a vector pointing in the direction of increased loss. And so in gradient descent, we are modifying p.data by a small step size in the direction of the gradient. So the step size, as an example, could be like a very small number, like 0.01 is the step size, times p.grad, right? But we have to think through some of the signs here. So in particular, working with this specific example here, we see that if we just left it like this, then this neuron's value would be currently increased by a tiny amount of the gradient.
So
the gradient is negative, so this value of this neuron would go slightly down. It would become like 0.8, 4 or something like that. But if this neuron's value goes lower, that would actually increase the loss. That's because the derivative of this neuron is negative. So increasing this makes the loss go down. So increasing it is what we want to do instead of decreasing it. So basically what we're missing here is we're actually missing a negative sign. And again, this other interpretation, and that's because we want to minimize the loss. We don't want to maximize the loss. We want to decrease it. And the other interpretation, as I mentioned, is you can think of the gradient vector, so basically just the vector of all the gradients, as pointing in the direction of increasing the loss. But then we want to decrease it. So we actually want to go in the opposite direction. And so you can convince yourself that this sort of like does the right thing here with the negative, because we want to minimize the loss. So if we nudge all the parameters by a tiny amount, then we'll see that...
So I guess this is the equivalent of a super small training run of a neural network.
This data will have changed a little bit. So now this neuron is a tiny amount greater value. So 0.854 went to 0.857. And that's a good thing because slightly increasing this neuron.
So now the loss should be lower than 4.84.
Data makes the loss go down according to the gradient. And so the correcting has happened sign-wise. And so now what we would expect, of course, is that because we...
My question would be like, why not, how do you decide this number, this small number? I mean, I do understand intuitively that if you went with like large numbers, you could maybe like overshoot it or overtune it. Like, the reasoning for going for with a small number is that you just do iterative improvement and you measure each step. If you just did big jumps, you have less control basically and less ability to measure. But then again, why not go with something that is still a small number, but like 0.1, which is 10 times bigger than 0.01? Yeah, I don't know. I don't have that knowledge.
We've changed all these parameters. We expect that the loss should have gone down a bit. So we want to reevaluate the loss. Let me basically, this is just a data definition that hasn't changed, but the forward pass here of the network, we can recalculate. And actually, let me do it outside here so that we can compare the two loss values. So here, if I recalculate the loss, we'd expect the new loss now to be slightly lower than this number. So hopefully what we're getting now is a tiny bit lower than 4.84.
Nice.
4.36.
That's a lot lower.
And remember, the way we've arranged this is that low loss means that our predictions are matching the targets. So our predictions now are probably slightly closer to the targets. And now all we have to do is we have to iterate this process. So again, we've done the forward pass, and this is the loss. Now we can loss that backward. Let me take these out, and we can do a step size. And now we should have a slightly lower loss. 4.36 goes to 3.9. And okay, so we've done the forward pass.
So this is basically training the model. This is like tuning it. Not really fine tuning, because that's, after the training run. But I mean, maybe this could also be called fine tuning. I don't know. I don't know what like the exact difference in the terminology is. Because from my understanding, fine tuning is when you have the weights already. But I guess we do have weights. So maybe this is the fine tuning, then rather the training. Because we did the forward pass, we did the backpropagation. So yeah, maybe we have trained this small multi-layer perceptron, and now we're fine-tuning it.
Pass, here's the backward pass, nudge. And now the loss is 3.66, 3.47. And you get the idea, we just continue doing
this. Is actually addictive. What the heck?
This. And this is gradient descent. We're just iteratively doing forward pass.
So obviously you wouldn't manually press Control Shift Enter every time. You would put this into a loop, measuring the loss, and then you can decide when to stop training when you're satisfied with the loss.
Pass, backward pass, update. Forward pass, backward pass, update. And the neural net is improving its predictions. So here, if we look at ypred now, ypred, we see that this value should be getting closer to 1. So this value should be getting more positive, these should be getting more negative, and this one should be also getting more positive. So if we just iterate this a few more times, actually we may be able to afford to go a bit faster. Let's try slightly.
Oh, so he did exactly what I was wondering about. Let's see.
Higher learning rate. Oops, okay, there we go. So now we're at 0.31. Actually we may be able to.
So we went from 2.5. So this is the danger of going with a too much of a, too high of a number, is that you can actually increase the loss instead of decreasing it.
To afford to go a bit faster. Let's try a slightly higher learning rate. Oops, okay, there we go. So now we're at 0.31.
So now we've made the neural network worse because we've increased the loss.
If you go too fast, by the way, if you try to make it too big of a step, you may actually overstep. It's overconfidence. Because again, remember, we don't actually know exactly about the loss function. The loss function has all kinds of structure, and we only know about the very local dependence of all these parameters on the loss. But if we step too far, we may step into, a part of the loss that is completely different. And that can destabilize training and make your loss actually blow up even. So the loss is now 0.04. So actually, the prediction is a loss that is completely different. And that can destabilize training and make your loss actually blow up even.
Wait, what? But this run, made the loss go down a lot. Is that just pure luck?
So the loss is now 0.04. So actually, the predictions should be really quite close. Let's take a look. So you see how this is almost 1, almost -1, almost 1. We can continue going. So Yep, backward, update. Oops, there we go. So we went way too fast. And
so now you would make these numbers again smaller and continue, I guess.
We actually overstepped. So we got too eager. Where are we now? Oops.
Oh my god.
7e-9. So this
is e-9. So this is ultra small.
Very, very low loss.
So this should be basically perfect.
And the predictions are basically perfect.
Nice. My prediction of his next words was basically perfect.
So somehow we were doing way too big updates and we briefly exploded, but then somehow we ended up getting into a really good update. Oops, there we go. So we went way too fast and too big updates and we briefly exploded, but then somehow we ended up getting into a really good spot. So usually this learning rate and the tuning of it is a subtle art. You want to set your learning rate. If it's too low, you're going to take way too long to converge. Yeah. But if it's too high, the whole thing gets unstable and you might actually even explode the loss.
So what I'm wondering is whether in the training of like the biggest LLMs, right, OpenAI, Anthropic, whatever, whether this number 0.01, well, negative 0.01, is actually set dynamically, right? Because right now it's hard coded in, but what if they're measuring like how unstable the loss function is, and then, you know, lowering or increasing that number based, you know, dynamically, like as the model is training. I think that's probably how they do it rather than hard coding it in.
Depending on your loss function. So finding the step size to be just right, it's a pretty subtle art sometimes when you're using sort of vanilla gradient descent. But we happen to get into a good spot. We can look at n-dot parameters. So this is the setting of weights and biases that makes our network predict the desired targets very, very close. And basically, we've successfully trained a neural net. Okay, let's make this a tiny bit more respectable and implement an actual training loop and what that looks like. So this is the data definition that stays. This is the forward pass. So for k in range, you know, we're going to take a bunch of steps. First, you do the forward pass. We validate the loss. Let's reinitialize the neural net from.
So obviously, so far, we've only done it manually, running it until it's good enough. But you know, the proper way is to do it in a for loop, and actually, so you can have more control and it's automated.
From scratch. And here's the data. And we first do the forward pass, then we do the backward pass. And then we do an update. That's gradient descent. And then we should be able to iterate this, and we should be able to print the current step, the current loss. Let's just print the sort of number of the loss. And that should be it. And then the learning rate, 0.01 is a little too small. 0.1 we saw is like a little bit dangerously too high. Let's go somewhere in between. And we'll optimize this for not 10 steps, but let's go for, say, 20 steps. Let me erase all of this junk. And
so let me implement this as well. Reconnect the runtime. Then let's see where we're at. If the neuron separated. Okay, so I need to update this. Be multidimensional. Run. Oh, run all. Yeah. When you disconnect the runtime, you need to run everything. Otherwise, MLP is not defined. Multi-layer perceptron. Okay, now it works. And obviously, this is a random number each time, because we are setting a random number in the constructor. Let's run this. Okay. And now This is the for loop.
And let's run the optimization. And you see how we've actually converged slower in a more controlled manner and got to a loss that is very low.
By the way, if you're not familiar with math, we're getting an error. Int and value. Something in our neuron class does not. Or is it even higher in the value class? Maybe I forgot to update this. Okay. And here brings 0.1. So the loss is converging. It is going to 0, but not as fast as it could go. What we could do is do further steps instead. That's much better. 0.07 though. Still kind of weak. We do 50 steps. Nah, do 0.2. Is that too unstable? It's still getting lower. So we could try. Yeah. But what I wanted to say is like this notation. I'm not sure what the proper terminology for it is, but we can just ask Perplexity. What is the proper terminology for this math notation, specifically when E is included to depict very small numbers? Basically, times 10 to the power of negative like 11 or something. The proper terminology, scientific notation, or more specifically, exponential notation. In this notation, numbers are expressed as coefficient multiplied by 10 raised to an integer power. The E is shorthand for x 10 to the power. So yeah, 10 to the power of negative 11, which, you know, if you do like 10 to the power of 6, that's million, right? 10 to the power of 6. Yes, so that's basically divided by million, 10 to the power of negative 6. And if we go like, you know, million, billion, trillion, you basically divide it by trillion. So 1.437 blah 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 divided by trillion. They're very close to 0. Four point 4.20 times 10 to the power of minus 13. Yeah, this is the easiest way to depict very small numbers. As you can see, it only started doing that at 10 to the power of negative 5. For that, it just went with the zeros. So 3 zeros is still readable, but I guess 4 zeros is no longer readable. Interesting.
So I expect Micrograd to be quite good. There we go.
I wonder why he got such low loss compared to me. See, I mean, I haven't even reached the scientific notation. Not disappointing. I don't know.
And that's it. Okay, so this is kind of embarrassing, but we actually have a really terrible bug in here. And it's a subtle bug, and it's a very common bug. And I can't believe I've done it for the 20th time in my life.
Okay, I guess this part of code not implemented. But what is it? This is like so nice to see that even the highest of levels, like AI researchers, don't get better than Andrej Karpathy. even the best of the best still make errors, still, you know, have bugs in their code. And that's like, makes it less intimidating, makes it more approachable.
Especially on camera. And I could have reshot the whole thing, but I think it's pretty funny. And, you know, you get to appreciate a bit what working with neural nets maybe is like sometimes. We are guilty of a common bug. I've actually tweeted the most common neural net mistakes a long time ago now. And I'm not really going to explain any of these except for we are guilty of number 3. You forgot to zero grad before dot backward. What is that? Basically what's happening, and it's a subtle bug, and I'm not sure if you saw it, is that all of these weights here have a dot data and a dot grad. And the dot grad starts at 0. And then we do backward and we fill in the gradients. And then we do an update on the data, but we don't flush the grad. It stays there. So when we do the second forward pass and we do backward again, remember that all the backward operations do a plus equals on the grad. And so these gradients just add up and they never get reset to 0. So basically we didn't zero grad. So here's how we zero grad before backward. We need to iterate.
Okay, I still don't really understand why that's necessary. Let's just try taking this screenshot and having Perplexity explain that. Explain mistake number 3 and why that's so crucial. I wish there was even more steps here, because like right now it's analyzing the image, and that should have been a step. Because like I don't like waiting with nothing happening on screen. This is a crucial step in the training process of neural networks, and here's why. Gradient accumulation. PyTorch accumulates gradients by default. This means that if you don't zero out the gradient before calling backwards, the new gradients will be added to the existing ones from previous iterations. Incorrect updates. Without zeroing gradients, the optimizer would update the weights based on the sum of all previous gradients, not just the current batch. This leads to incorrect weight updates and can significantly hinder the learning process. Zeroing gradients ensures that each batch is treated independently, which is crucial for stochastic gradient descent and its variance. Oh, because if we didn't reset it, I guess the first batch would have way too much of an effect and just like pollute everything. It allows the model to learn from the current batch without interference from its previous batches. Okay.
So here's how we zero grad before backward. We need to iterate over all the parameters. And we need to make sure that p.grad is set to 0. We need to reset it to 0, just like it is in the constructor. So remember all the way here for all these value nodes, grad is reset to 0. And then all these backward passes do a plus equals on that grad. But we need to make sure that we reset these grads to 0 so that when we do backward, all of them start at 0 and the actual backward pass accumulates the loss derivatives into the grads. So this is zero grad in PyTorch. And we'll get a slightly different optimization. Let's reset the neural net. The data is the same. This is now, I think, correct. And we get a much more...
Yeah, now it makes sense. Now the numbers are much closer to what we've got, you know. Not super, like, hyper optimized towards 0 scientific notation, but more manageable. Yeah. Notice that every time we run it, it accumulates. You know, like basically, like the 0 step is, you know, last time's step. So we're still improving the loss. So we're like doing another 20 runs or whatever. This is so addictive, man. I see why people become AI researchers, just watching the... Imagine like launching GPT-5 training and watching the loss function go down. Like, wow, how addictive is that? watching your model that you've built, that you spent thousands of hours on, learn and improve and get smarter. Fascinating, man.
We get a much more slower descent. We still end up with pretty good results, and we can continue this a bit more to get down lower and lower and lower. Yeah. So the only reason that the previous thing worked, it's extremely buggy. The only reason that worked is that this is a very, very simple problem, and it's very easy for this neural net to fit this data. And so the grads ended up accumulating, and it effectively gave us a massive step size, and it made us converge extremely fast. But basically now we have to do more steps to get to very low values of loss and get YPRED to be really good. We can try to step a bit greater.
Yeah, so what if we just, do what Karpathy did, but we don't print it out, right? Like, we don't have to print it out. We just print it out at the end. The last one. Now we can do 300. Who's running for a bit. And suddenly we're using scientific notation. Beautiful. Now maybe, let's do again. Is it getting lower? 6, okay. It is getting lower. Let's try 3000. That's gonna obviously take a few seconds, since we're using rented GPUs, actually for free from Google. But this is training the model. 12 seconds. And this is super small, like what, 41 Neuron multi-layer perceptron. Super small. Still takes 12 seconds on this free GPU from Google. You can see how big LLMs are expensive to train. Let's chill it out to 300. That was pretty manageable. You were seeing how it's still improving, although slowing down significantly. Yeah.
Yeah, we're going to get closer and closer to 1, -1, and 1. So working with neural net.
Let's do YPRED. Yeah, we're very close.
This is sometimes tricky because you may have lots of bugs in the code, and your network might actually work, just like ours worked. But chances are is that if we had a more complex problem, then actually this bug would have made us not optimize the loss very well. And we were only able to get away with it because the problem is very simple. So let's now bring everything together and summarize what we learned. What are neural nets? Neural nets are these mathematical expressions, fairly simple mathematical expressions in the case of multi-layer perceptron, that take input as the data, and they take input the weights and the parameters of the neural net. Mathematical expression for the forward pass, followed by a loss function, and the loss function tries to measure the accuracy of the predictions. And usually the loss will be low when your predictions are matching your targets, or where the network is basically behaving well. So we manipulate the loss function so that when the loss is low, the network is doing what you want it to do on your problem. And then we backward the loss, use backpropagation to get the gradient, and then we know how to tune all the parameters to decrease the loss locally. But then we have to iterate that process many times in what's called the gradient descent. So we simply follow the gradient information, and that minimizes the loss, and the loss is arranged so that when the loss is minimized, the network is doing what you want it to do. And yeah, so we just have a blob of neural stuff, and we can make it do arbitrary things. And that's what gives neural nets their power. This is a very tiny network with 41 parameters, but you can build significantly more complicated neural nets with billions, at this point, almost trillions of parameters. And it's a massive blob of neural tissue, simulated neural tissue, roughly speaking. And you can make it do extremely complex problems. And these neural nets then have all kinds of very fascinating emergent properties in when you try to make them do significantly hard problems. As in the case of GPT, for example, We have massive amounts of text from the internet, and we're trying to get a neural net to take like a few words and try to predict the next word in a sequence. That's
one thing that people don't understand, which I actually learned from Ilya Sutskever, is that the reasons the models are so smart and can do reasoning and stuff like that is because in order to be excellent at the next token prediction, which is what they do, they have to learn to understand the user, right? You cannot predict the next token exceptionally well if you don't understand the text, if you don't understand what the user means. So intelligence is almost, as Andrej is saying, an emergent property. Because all they're trying to do is predict the next token, but they have to become intelligent in the process to do that super well.
That's the learning problem. And it turns out that when you train this on all of internet, the neural net actually has like really remarkable emergent properties, but that neural net would have hundreds of billions of parameters. But it works on fundamentally the exact same principles. The neural net, of course, will be a bit more complex, but otherwise the evaluating the gradient is there and will be identical, and the gradient descent would be there and would be basically identical, but people usually use slightly different updates. This is a very simple stochastic gradient descent update. And the loss function would not be a mean squared error. They would be using something called the cross entropy loss for predicting the next token. So there's a few more details, but fundamentally the neural network setup and neural network training is identical and pervasive. And now you understand intuitively how that works under the hood. In the beginning of this video, I told you that by the end of it, you would understand everything in Micrograd and then we'd slowly build it up. Let me briefly prove that to you. So I'm going to step through all the code that is in Micrograd as of today. Actually, potentially some of the code will change by the time you watch this video because I intend to continue developing Micrograd. But let's look at what we have so far at least.
Here it has 2.2k stars, but I guarantee you that thanks to this video, it blew up way more. Yeah, 9.4k. But yeah. Let's see what's Andrej's most popular project. LLM.C, Nano GPT, Llama 2C. Simplest, faster repository for training, fine-tuning, medium-sized. I need to build this. Honestly, I need to do all of Andrej Karpathy's training. We'll see how well this video does. If it does well, I will just do all of his tutorials. 2010, first commit on GitHub. 2011, 2012, more activity. 2013, not that much. 2014, a lot more. 2015, a lot more. 16, time is Tesla. 23, 24. Okay, so now he's cooking. Well, now he seems to be on vacation or something. But yeah, ever since he left OpenAI, been quite productive. But yeah, I mean, in terms of repositories, is there a sort by most popular? Stars, Nano GPT. Updated 2 hours ago. Okay.
Init.py is empty. When you go to engine.py, that has the value. Everything here you should mostly recognize. So we have the .data.grad attributes, we have the backward function, we have the previous set of children and the operation that produced this value. We have addition, multiplication, and raising to a scalar power. We have the ReLU nonlinearity, which is a slightly different type of nonlinearity than tanh that we used in this video. Both of them are nonlinearities, and notably tanh is not actually present in Micrograd as of right now, but I intend to add it later. We have the backward, which is identical, and then all of these other operations, which are built up on top of operations here. So values should be very recognizable, except for the nonlinearity used in this video. There's no massive difference between ReLU and tanh and sigmoid and these other nonlinearities.
Let me understand ReLU. Help me understand the ReLU function used in AI ML. Explain in simple terms. ReLU stands for rectified linear unit. One of the most commonly used activation functions in artificial neural networks and machine learning models. Here's how ReLU works in simple terms. It takes an input value. If the input is positive, greater than 0, ReLU outputs that same value. If the input is negative, less than or equal to 0, ReLU outputs 0. Basically looks like this. You can think of ReLU like a simple on-off switch. For positive inputs, it's on, lets the value pass through unchanged. For negative inputs, it's off and blocks the value, outputting 0 instead. Mathematically, it can be expressed as function of x max 0 x. Main advantages of ReLU: simplicity, non-linearity, sparsity.
They're all roughly equivalent and can be used in MLPs. So I use 10H because it's a bit smoother and because it's a little bit more complicated than ReLU, and therefore it's stressed a little bit more the local gradients and working with those derivatives, which I thought would be useful. NN.py is the neural networks library, as I mentioned. So you should recognize identical implementation of Neuron, Layer, and MLP. Notably, or not so much, we have a class module here. There's a parent class of all these modules. I did that because there's an nn.module class in PyTorch, and so this exactly matches that API. And nn.module in PyTorch has also a zero grad, which I refactored out here.
It's amazing, like how he's thinking ahead that we're going to be using PyTorch and that this is basically an education step towards that.
So that's the end of Micrograd, really. Then there's a test, which you'll see basically creates two chunks of code, one in Micrograd and one in PyTorch, and we'll make sure that the forward and the backward paths agree identically. For a slightly less complicated expression and slightly more complicated expression, everything agrees. So we agree with PyTorch on all of these operations. And finally, there's a demo.ipymb here, and it's a bit more complicated binary classification demo than the one I covered in this lecture. So we only had a tiny data set of 4 examples. Here we have a bit more complicated example with lots of blue points and lots of red points. And we're trying to, again, build a binary classifier to distinguish two-dimensional points as red or blue.
So I guess here is like estimating the function approximate.
It's a bit more complicated MLP here it's a bigger MLP. The loss is a bit more complicated because it supports batches. So because our dataset was so tiny, we always did a forward pass on the entire dataset of 4 examples. But when your dataset is like 1,000,000 examples, what we usually do in practice is we basically pick out some random subset. We call that a batch. And then we only process the batch forward, backward, and update. So we don't have to forward the entire training set. So this supports batching because there's a lot more examples here. We do a forward pass. The loss is slightly more different. This is a max margin loss that I implement here. The one that we used was the mean squared error loss because it's the simplest one. There's also the binary cross entropy loss. All of them.
Yeah, I mean, if you think what we did in this video was, I mean, it was complex, but like nowhere near the top levels of machine learning and deep learning.
Can be used for binary classification and don't make too much of a difference in the simple examples that we looked at so far. There's something called L2 regularization used here. This has to do with generalization of the neural net and controls the overfitting in machine learning setting, but I did not cover these concepts in this video, potentially later. And the training loop you should recognize. So forward, backward, with zero grad, and update, and so on. You'll notice that in the update here, the learning rate is scaled as a function of number of iterations, and it shrinks. And this is something called learning rate decay. So in the beginning, you have a high learning rate, and as the network sort of stabilizes near the end, you bring down the learning rate to get to some of the fine details in the end.
Oh, so I guess I was right when I said before that it's dynamically changed. Yeah.
This near the end, you bring down the learning rate to get to some of the fine details in the end. And in the end, we see the decision surface of the neural net, and we see that it learned to separate out the red and the blue area based on the data points. So that's the slightly more complicated example in the demo.ipymb that you're free to go over. But yeah, as of today, that is Micrograd. I also wanted to show you a little bit of real stuff so that you get to see how this is actually implemented in a production grade library like PyTorch. So in particular, I wanted to find and show you the backward pass for 10H in PyTorch. So here in Micrograd, we see that the backward pass for 10H is 1 minus t squared, where t is the output of the 10H of x, times Autograd, which is the chain rule. So we're looking for something that looks like this. Now, I went to PyTorch, which looks like this. Now,
yeah, I mean, the PyTorch GitHub, you can definitely spend hundreds of hours.
I went to PyTorch, which has an open source GitHub code base, and I looked through a lot of its code. And honestly,
Jesus, man.
I spent about 15 minutes and I couldn't find 10H. And that's because these libraries, unfortunately, they grow in size and entropy. And if you just search for 10H, you get apparently 2,800 results and 406 files. So I don't know what these files are doing, honestly, and why there are so many mentions of 10H. But
when even Karpathy is confused, you know, you've got a complex code base.
Fortunately, these libraries are quite complex. They're meant to be used, not really inspected. Eventually, I did stumble on someone who tries to change the 10H backward code for some reason. And someone here pointed to the CPU kernel and the CUDA kernel for 10H backward. So basically it depends on if you're using PyTorch on a CPU device or on a GPU, which these are different devices and I haven't covered this. But this is the 10H backward kernel for CPU. And the reason it's so large is that number one, this is like if you're using a complex type, which we haven't even talked about, if you're using a specific data type of bfloat16, which we haven't talked about. And then if you're not, then this is the kernel, and deep here we see something that resembles our backward pass. So they have a times 1 minus b squared. So this b here must be the output of the 10H, and this is the out.grad. So here we found it, deep inside PyTorch on this location, for some reason inside binary ops kernel, when 10H is not actually.
Yeah, so that's like 7 folders deep in a C++ file that has 1,182 lines of code. Yeah.
Binary op. And then this is the GPU kernel. We're not complex. We're here, and here we go with one line of code. So we did find it, but basically, unfortunately, these code bases are very large, and Micrograd is very, very simple. But if you actually want to use real stuff, finding the code for it, you'll actually find that difficult. I also wanted to show you a little example here where PyTorch is showing you how you can register a new type of function that you want to add to PyTorch as a Lego building block. So here, if you want to, for example, add a Legendre polynomial 3, here's how you could do it. You will register it as a class that subclass is torch.autograd.function. And then you have to tell PyTorch how to forward your new function and how to backward through it. So as long as you can do the forward pass of this little function piece that you want to add, and as long as you know the local derivative, the local gradients, which are implemented in the backward, PyTorch will be able to backpropagate through your function. And then you can use this as a Lego block in a larger Lego castle of all the different Lego blocks that PyTorch already has. And so that's the only thing you have to tell PyTorch, and everything would just work. And you can register new types of functions in this way, following this example. And that is everything that I wanted to cover in this lecture. So I hope you enjoyed building out Micrograd with me. I hope you find it interesting, insightful, and yeah, I will post a lot of the links that are related to this video in the video description below. I will also probably post a link to a discussion forum or discussion group where you can ask questions related to this video, and then I can answer or someone else can answer your questions. And I may also do a follow-up video that answers some of the most common questions. But for now, that's it. I hope you enjoyed it. If you did, then please like and subscribe so that YouTube knows to feature this video to more people. And that's it for now. I'll see you later.
The fact that this video is free to watch feels illegal. It took me, many hours to get through it. I don't know what the final duration will be, but I've learned insane amount. This is legit years worth of knowledge, condensed, compressed into 6-7 hours. I don't know. This is literally like college level education, maybe even PhD level education for free on YouTube. Huge thanks to Andrej Karpathy for making this video, and huge thanks to you, because if you're watching this, you've probably watched the entire thing. So yeah, thank you so much, and have a great rest of the day.